Okay, so we really want to get a very direct, visual, geometric understanding of the nature of these perfect shapes, which are called regular polytopes, and the kind of symmetries and structure that they have. And here is where something happens which is so extraordinary and powerful and beautiful that it's difficult for me to convey at this point. So basically, there's a certain kind of mathematical tool that we're going to use, something called a Coxeter group. And when we use this tool, we're going to instantly understand all of the symmetries of all of these regular polytopes in a totally visual way. It's really difficult to convey just how powerful this notion is. So you don't need any prerequisites to follow this video. So let us begin. Now, basically, we're interested in understanding what are the most perfectly symmetric shapes possible in every dimension. And so we're going to start in 2 dimensions. So the kind of shapes I want to study are things like these polygons, things that have a finite number of vertices and straight edges and discrete bits. Okay, so there are other shapes like a circle, which is highly symmetric, because basically if you have a circle, you can rotate it by any amount, and that can be considered to be a sort of symmetry of the circle. So the circle has an infinite amount of symmetry in some sense, but I'm more interested in these kind of discrete shapes. And so when we're in 2-dimensional space, these regular shapes correspond to these polygons here, these so-called regular polygons. Now, I'm sure you all know about these already. It is a very good idea to focus intensely on these kind of structures, because basically as we go into higher dimensions, we see that these forms of the triangle and the square and the pentagon and so on are basically occurring in higher dimensions. And so it's the usual story in mathematics that we want to make very sure that we understand the kind of basic cases before we move on up. I mean, saying that, I'm actually going to quite quickly ascend to discussing higher dimensional space. But when we're in 2 dimensions, the most perfect shapes possible are these regular polygons. Okay, so we have the regular triangle, the regular square, the regular pentagon, and so on. So let me just give a rough explanation about some of the words that I've just been using. So I keep talking about symmetry. What do I mean by symmetry? Well, I want to work at a kind of intuitive level for most of this video, and I'd say that intuitively, a symmetry of the shape is a kind of transformation that we can do on that shape that leaves the shape looking the same afterwards. So for example, if we have a square and then we rotate it by a quarter of a turn, it's going to look the same. And so doing a quarter of a turn clockwise will be a particular symmetry of a square. Or another example is if we have, let's say, that triangle there, and then we reflect it about this line here. This is another symmetry. This is another operation we can do on our triangle, which basically leaves it looking the same afterwards. I mean, in a sense, as we're going to see, these reflections are actually quite a bit more interesting than the rotations. One of the themes of this video is basically that we can use reflections to understand so much about geometry. We can use them to understand rotations. We can use them to understand all sorts of symmetries that these shapes have. But I'd like you to think for a moment about what life is like for a being that lives in 2 dimensions. Let's have some sympathy for the ants here. So if you were a 2-dimensional being, you would know what an equilateral triangle is, much as we know what a tetrahedron is because we live in 3D. And such a 2-dimensional being could surely understand this idea of rotation, okay? Because if you have, let's say, a square in 2D and you rotate it, well, the square can sort of stay in the plane as it rotates. We can really understand the whole phenomenon of rotation while staying inside of 3D. But it's a bit different for reflection in some sense. You know, if I had a cardboard blue triangle and I wanted to illustrate what happens when I do this reflection on it, the easiest thing I could do would be to pick up the triangle in the 3rd dimension and physically flip it over and plonk it back down. But that's not as easy to describe from within the plane. So there's something already very interesting happening here. Anyway, we're going to get into these matters later. Another thing that I'd like to sketch a sort of definition of is what I mean here by a regular polygon. And so polygon means many sides. For example, we have a triangle. We could say that that's a 3-gon because it has 3 sides. Now, there are many different triangles. There are some triangles which are very long and pointy, and there's also triangles like this blue one here that are totally symmetric. All of the sides have the same length and all of the angles are the same. Every edge looks the same as every other edge. Every vertex looks the same as every other vertex. That's what I mean by a regular polygon. And you can see here that when we have a number of sides, which might be 3 or 4 or more, we're going to be able to find a regular polygon that has that many many sides. And these are our first examples of regular polytopes. Basically, a polytope is a sort of generalization of a polygon. A polytope may exist in higher dimensional space. So you can imagine, basically, if we get the idea of a polygon and then we kind of think about something analogous, but it might be in 3D or 4D or whatever, that would be a polytope. And a regular polytope is a polytope which is as symmetric as possible. If we look at any sort of part of the polytope of any particular dimension, it's going to look the same as any other part of the polytope of the same dimension. We're going to get into this later. But hopefully you're comfortable with this two-dimensional case. Now, I just want to say one more little thing before we start climbing up to higher dimensions, and that is that there's a certain kind of notation that's going to be extremely useful for us. When we have one of these regular polytopes, we can write this notation to represent it, and it's called a Schläfli symbol. So let's start with this two-dimensional case. So if we have, for example, this triangle here, the Schläfli symbol for that is a 3 in curly brackets, because this is a regular triangle with 3 sides. Similarly, our square is having a Schläfli symbol, which is a 4 in curly brackets, and so on. And so more generally, when we have a regular polygon, so P would be a number, the number of sides we have, well, the Schläfli symbol for that is going to be a P in curly brackets. So that's enough of that. Let's go to a high dimension. Let's see what happens in 3D. What are the regular polytopes in 3D? And here we're looking at polyhedra. That means many faces, okay? So these three-dimensional shapes have vertices, edges, and faces. And in 3 dimensions, this family of shapes that are as symmetric as possible is really quite different to the case in 2D. You see, in the 2-dimensional case, we found that there were infinitely many of these regular polygons. But in 3 dimensions, when we classify the regular polyhedra, the shapes that are as symmetric as possible, we find that there are only 5, okay? And here they are. They're sometimes called the Platonic solids. So there's lots of shapes in 3D with a large amount of symmetry, but when we insist that things are absolutely as symmetric as possible, in the sense that every vertex looks like every other vertex, every edge looks like every other edge, every face looks like every other face, well, in that case, we find that there are only 5 shapes that fit this criteria, and here they are. So these Platonic solids have fascinated curious people throughout the ages, because it's really a very remarkable thing. Like, why are there only 5 of them? Well, anyway, for now, let's just have a closer look at each of these. This one here is probably the most familiar to you. It's the cube. So it has square faces, and there's 3 of them meeting at every corner. So we humans love cubes. It seems like almost everything that we design in engineering and architecture has something to do with cubes. We seem to really like this kind of rectilinear geometry. And I think that this kind of geometry of the cube and the kind of higher dimensional versions of that really have a huge influence on how we think and how we design things, and even how we do things like computing. Now, even though the cube might be the most familiar of these regular polyhedra, it's not the simplest. The simplest one is the tetrahedron here. So the tetrahedron is a triangular-based pyramid. It's a really remarkable shape. It only has 4 vertices, which is the minimum possible, and it only has 4 faces, and I would really say it's the very simplest 3-dimensional form. Now, hopefully you can see that the cube and the tetrahedron are kind of like the 3-dimensional analogues of the square and the equilateral triangle that we met, and we're going to see that these shapes have analogues in higher dimensions as well. Anyway, let's take a look at some more of these regular polyhedra. So the next one I want to talk about is this octahedron here. So this again has triangular faces, but now it has 4 triangles meeting at every vertex. An easy way to make an octahedron is if you get a square-based pyramid and then you glue another square-based pyramid onto the bottom, pointing in the opposite direction. And we're going to see later that the cube and the octahedron have a lot in common. They're kind of like twins. They're actually what we call duals of each other. We'll talk about that soon. And then the final 2 regular polyhedra are perhaps the most interesting. This one here is the dodecahedron. It has 12 pentagons as its faces, and it's really a remarkably beautiful form. So the dodecahedron has mystified and fascinated people for thousands of years because it's so extraordinary that such a large, complex form fits this criteria of being one of the 5 most symmetric shapes possible. And then the final regular polytope in 3D space is the icosahedron. So this is the dual of the dodecahedron, and it has 20 triangular faces. So it's again an extraordinary shape. So I could talk for hours about these Platonic solids, but I really want to get to the higher dimensional situations. So I'm going to move on. So there's just a few more comments I want to make about these regular polyhedra before we ascend to the wonders of 4 dimensions. And basically, I want to mostly talk about phenomena that we're going to see again in higher dimensional space. So the first one is duality. So this is a really, really lovely idea. Basically, if we get one of these regular polyhedrons, for example, a cube, and then we mark the center of each face and we draw a vertex there, then those vertices that we've just drawn are going to be the vertices of another regular polyhedron. In this case, when we start with a cube, the polyhedron that we draw inside is going to be the octahedron. And so the octahedron is the dual of the cube. And you can also see on the right that it works the other way around. So if we get an octahedron and we dualize that, we get our cube back again. So this is really remarkable because, for one thing, it means that from the point of view of symmetry, really the cube and the octahedron are kind of the same. They have the same symmetries, and in a sense, it's the same kind of information which goes into both of those forms. So each of our polyhedra has a dual. The dual of the dodecahedron is the icosahedron and vice versa. And another very interesting fact is that if we get a tetrahedron and we dualize that, what do we get? Well, we get another tetrahedron, kind of a tetrahedron that's pointing the other way, if you like. You can see the idea illustrated up here. So this isn't too important for today's video, but I'll just briefly say for people that know, we can think about this dualization in terms of poles and polars. So if you followed my videos on projective geometry, you'll know that, for example, in 2 dimensions, you can use a circle to translate between points and lines. And actually, the same idea generalizes to higher dimensions. You can use a sphere to convert points into planes and vice versa. Anyway, I'm not going to explain that, and you don't need to know it to follow this video. But being able to do this dualization gives us access to lots more interesting geometry. So if you take a cube and you dualize it, you get this little octahedron inside. Now you can make that octahedron bigger until you have a configuration like this. Okay, so this is a remarkable structure. It's sometimes called the cube octahedron compound. Actually, we can get this kind of thing directly by doing that kind of reciprocation or polarity thing using a sphere of the right kind of radius. But that's the last I'll say about that. I just want you to have a look at this picture here and to notice a very interesting thing, which is that we have a cube here and an octahedron. And if we have a look at one of the edges of the cube and where the middle of that edge is, you can see that that coincides with the middle of an edge of the octahedron. And so when we have this sort of shape, we can ask some interesting questions. For example, what is the sort of intersection or the common volume between this red cube and this green octahedron? And the answer to that is this shape on the right. And this is sometimes called the Cuboctahedron. It has 12 vertices and its faces are squares and triangles. So this is a remarkable shape as well. And we're going to see this come up again later. Now, there's just one more thing I want to mention before we get up to 4 dimensions, and it has to do with this remarkable compound here. So remember, the dual of a tetrahedron is a tetrahedron. And so if we play a similar game to above, we get this kind of configuration. Now, these 2 interlocking tetrahedra form this celebrated shape called the stellar octangular. And one thing I'd like you to notice here is that we have this cube which kind of envelops this shape. Okay, so this is really a structure that it's well worth meditating on. And there's another very, very easy way to think about this structure. Okay, so forget about the tetrahedra temporarily and just think about a cube. Okay, so if you have a cube, then you can pick a vertex of the cube. For example, you might pick this bottom vertex here that's closest to us, and you can mark that as pink. And now that pink vertex is one of the corners of the cube. Now, you don't mark the vertices that are linked to that pink vertex directly, but you do mark the vertices that are 2 hops away. So you end up marking this vertex and also the vertex that we can't see. So now you've marked 4 of the 8 vertices of the cube. You've marked every other vertex, and you've just selected the 4 vertices that form this pink tetrahedron here. So this kind of structure where you take a cube and you mark every other vertex is sometimes called a demicube. So since we're in 3 dimensions, this word demicube is a bit redundant. We might as well just call it a tetrahedron because that's what it is. So we're soon going to be going to higher dimensions and looking at hypercubes. And in that kind of context, these demicubes can have much more interesting forms. Okay, so I think we're ready for our ascent into 4-dimensional space. So I've discussed regular polygons and regular polyhedra. Now, they're both examples of regular polytopes. And regular polytopes are basically the same kind of idea, but in a general number of dimensions. So a polyhedron in 3 dimensions has vertices, edges, and faces, but soon we're going to be looking at polytopes in 4 dimensions. So they have vertices, edges, faces, and also 3-dimensional cells. An irregular polytope is a polytope that's as symmetric as it can possibly be. We'll say more about that later. Anyway, let's go into 4-dimensional space. Now we're going to start in a very humble way with something that's 0-dimensional. So if it's 0-dimensional, there's no directions that you can move in. So the only thing that we can have is a point. And now we want to move up in dimension. So we're going to take our point and we're going to move it in a new direction. And we're going to look at what kind of trail gets made. Okay, this is a 1-dimensional shape. Now let's keep going. Let's keep pushing up the dimension. So to get into 2 dimensions, we're going to do the same thing again. We're going to take our line segments and we're going to move it in a new direction that's perpendicular to the direction we already have. And when we do that and we look at the trail that we get this shape here. This is our square. This is a regular polytope in 2 dimensions. Okay, so this is going well, so let's keep going. So we'll take our square and now we want to get something 3-dimensional. So with the square, we have these 2 directions, right and up. And now what we're going to do is move our shape in a new direction, perpendicular to everything we had before. And if we look at the kind of trail that we get when we move our square in this new direction, we get a cube, which is one of the 3-dimensional regular polytopes. But something that's truly remarkable is that we don't have to stop here. Now we can just continue the same kind of pattern and get something that's 4-dimensional. And it's easy to do. So in the cube, we have these 3 perpendicular directions, right, up, and forwards, or green, blue, and red. But let's continue the pattern and go into 4-dimensional space. So at the level of these pictures, this is easy to do. Okay, we just take our cube and then we imagine that we have another direction that's perpendicular to the 3 that we know. And then we just move our cube in that new direction and we look at the sort of trail that's formed. And now we have this, which is a 4-dimensional cube, also known as a tesseract. And this is one of the 4-dimensional regular polytopes. We're going to get very familiar with it. And so hopefully you can imagine that this same kind of construction process could be continued. Okay, we could make 5-dimensional hypercubes, 6-dimensional hypercubes, and so on. But I really want to stop here at 4 dimensions and try and build some kind of intuition about what's going on. So at first glance, I think some people can be quite bewildered by this idea of 4-dimensional space. I've noticed some people seem to go into some kind of a state of denial and sort of act like this 4-dimensional stuff isn't real or important. But I think these ideas are certainly important. Now, one thing we can do to really help our understanding is to make a sort of better picture of this tesseract. And so there are many ways to draw a tesseract. Much like if we come down by 1 dimension, there are many ways to draw a cube. Now, since a cube is a 3-dimensional shape, we can't really represent it properly with a 2-dimensional picture, but we can draw a sort of shadow or projection of it, and you've already seen me do that. But actually, the way I really like to draw cubes is the way I'm showing here, because notice that in this picture, the only places where 2 edges meet are at vertices, and I like that property. Now, I have heard that one of the ways that doctors analyze if people have brain damage is to ask them to draw cubes, and maybe if I drew this for a doctor, they might treat me in some special kind of way, but still I find this picture very useful. And so now we want to draw our tesseract, and so all I'm going to do is have 1 cube here, I'm going to draw another cube, and I'm going to connect corresponding vertices. And so here we have the result. This is another way to look at the tesseract. And this is a remarkably interesting structure. Okay, so it has vertices, it has edges, it also has these 2-dimensional faces. So here's an example, but there's something amazing that's happened now, which is that we have multiple 3-dimensional faces. These are also called cells. So actually this tesseract lives in 4-dimensional space. And so what you should imagine is that in here, for example, we have this 3-dimensional chamber or a 3-dimensional cube, and that's part of our tesseract in a totally analogous way to how with a 3-dimensional cube, we have these 2-dimensional squares which are forming the faces. With this tesseract, we have these 3-dimensional cubes which are forming these cells. And so if you think back to the 3D case for a moment, think about a cube, think about a dice, for example, well, that has 6 sides. It has 6 2-dimensional faces. And this tesseract, this is the 4-dimensional analog, this actually has 8 cells. It has 8 3-dimensional faces. So there's this cube in the middle here, there's also 6 cubes, like these are 4 of them, and then there's one in front and one behind. They're kind of hard to draw, but we're going to get a lot more intuition later when we look at some models and so on. And then in fact, the outside of this shape is thought of as constituting the 8th cubically shaped cell. We're going to get a lot more intuition for this later. So how are we to understand 4-dimensional space? Well, there's 2 very powerful methods that I want to talk about. The first is the method of dimensional analogy. The idea is that if we think about what happens when we go from 2 dimensions to 3 dimensions, this is something we're very familiar with, of course. Well, basically, a lot of the happenings in that case have a sort of analogy that occurs when we go from 3 dimensions to 4 dimensions. So in particular, one of the most powerful methods for understanding things in geometry is to imagine that you are living in whatever kind of shape there is. I think there's something about how the human mind works when we really imagine actually living in a particular place or space that really helps us to gain intuition. And so as a 3-dimensional person, I find this 4th dimension kind of hard to wrap my mind around. And so I want to use this idea of dimensional analogy to help me. So what I'm going to do is imagine that I was a 2-dimensional person. So imagine that I was an ant or something, and I was confined to living on a plane. So if I was confined to living on this grey plane here, then a good question is, could I understand what a cube is? Okay, if I have no idea about the idea of up, how can I understand the notion of a cube? Well, perhaps understanding some aspects of the cube might escape me, but I could certainly understand the idea of a shadow of a cube. And this is what you can see here. We have this 3D cube, and then its 2D shadow is being projected onto this plane here. And so if you imagine that you're a 2D person, well, you can basically see all the vertices and edges of this cube, so we can understand the connectivity, and we can kind of make a 2-dimensional model of this 3D cube, or, you know, a shadow or a model, whatever you want to call it. And basically something totally analogous happens when we go from 3D to 4D. So what I'm showing here is a 3-dimensional shadow of our tesseract. And you can see more clearly here that we have a cube in the middle, and we have these 6 kind of distorted cubes around the outside of that. And then we consider the very outside of this to be the final cubical cell of our tesseract. Now, if this idea that the outside of this shape should be thought of as a cube seems peculiar to you, then just take a look again at this case of a projection 1 dimension lower. Notice that for our 2-dimensional flatlander that lives in this plane, really the 6th face of our cube is sort of getting projected to the outside. And so, of course, really the tesseract lives in 4-dimensional space. If we're going to make a 3D picture of it, there's going to be some distortion. But if we rotate our tesseract in 4-dimensional space, then the 3D projection of it is going to change. And so there are many different 3D projections of our tesseract where it's distorted in different ways. Okay, so we can use this idea of dimensional analogy to understand about high-dimensional space. Another very powerful method is to use numbers and coordinates. To start talking about this, let's have a look at this 1-dimensional hypercube here, this line segment. How can we use numbers to describe where we are inside this shape? Well, it's very easy. We can just say that the left vertex is associated with -1, the right vertex is associated with the number 1, and then as we move along this line segment, that's just like changing our number from -1 to 1. And so the center of this line segment is going to be 0. So this is a particularly pleasant way to understand the line segments, because we have a number system that allows us to think about fractions and the kind of continuum of points between -1 and 1. That's the line segment. In fact, we can extend this idea. We can talk about numbers which are bigger than 1, and so they're sort of in line with our segment, but kind of beyond it within this extended orange line here. And so if we use our so-called real numbers, then we can talk about not only the integers like 0 and 1 and 2 and -1, you know, whole numbers. We can also have fractions, and maybe if we want to use real numbers, we can also include irrational numbers like pi or the square root of 2. Which actual number system we use is slightly controversial, but I'm going to talk about using the real numbers as most people do. So we write this scripty R symbol here to denote the set of all real numbers. And we can really think of the the real numbers as really corresponding to this one-dimensional infinite space. So a lot of mathematicians say, well, one-dimensional space basically is the same thing as this set of real numbers, because wherever you are in one-dimensional space can be described with a single coordinate, which basically tells you how far to the right of the origin 0 you are. So we can use the same kind of idea to understand two-dimensional space. We can use these coordinates. So if you have a point on the plane, a point in two-dimensional space, you could describe where that point is using an x-coordinate and a y-coordinate. So the x-coordinate tells you how many steps you have to go to the right from the origin, and the y-coordinate tells you how many steps up you have to go from the origin. And so recording those two numbers, x and y, gives you a point in two-dimensional space. And so it's a great way to think about 2D space. And so we can use these so-called Cartesian coordinates with x and y to say where we are in this two-dimensional space. And once again, this gives us a really powerful way to understand the structure of our now two-dimensional hypercube or square. So we can set things up so that the vertices of our square can be given coordinates like this, involving 1 and -1. So for example, this bottom left vertex has coordinates -1, -1, because to get to it from our origin here, we have to take one step to the left and then one step down. So using coordinates like this is very powerful, especially when we get into higher dimensional space. But you can see here that in the plane, we can describe where we are just using these two numbers, x and y. And so two-dimensional space corresponds to this set here that we write as r squared. What we're basically just saying here is that a point of two-dimensional space corresponds to a pair of real numbers, which is a member of this set here. This is the settable pairs of real numbers. That's why we have this 2 here in the top right corner. So we can carry on with this idea up into 3 dimensions. So if you have a point in 3-dimensional space, you can describe where it is with an x and a y and a z coordinate. So those are telling you how far to the right, how far up, and how far forwards from the origin you have to go to get to your particular location. So you could think of it like the first 2 numbers are telling you where your building is on the flat plane, and then the third number is telling you which floor of the building you're living on. Now, once again, we can use these 3D Cartesian coordinates to think about our cube in a very, very pleasant way. So in fact, we can set things up so that each of these 8 vertices of our cube have coordinates where each of the entries are either -1 or 1. So this is an extremely powerful way to think about the cube, or more generally hypercubes, because setting things up like this has all sorts of pleasant features. The very center of the cube has coordinates 0, 0, 0, which is very symmetric. If we're at this vertex here, which has coordinates -1, -1, -1, we see that if we want to walk along an edge of the cube, well, there are 3 different perpendicular directions we can go. And you see that traveling along each of those edges corresponds to varying one of the 3 entries in our coordinates. So if we travel along this green edge to the right, that would be taking 2 steps to the right. So we'd be changing the first entry of our coordinates, -1, into a 1. If we travel up, then we turn this second -1 into a 1. And what if we travel in the other direction? What point will we get to there? Well, we'll get to this point here, which has coordinates -1, -1, 1. But there's lots of other great things that we can do with these coordinates. So usually I'm a big advocate of geometric approaches, but I've got to say that this is one place where you can really do things using these coordinates and taking a kind of combinatorial approach to the hypercube. You can really get your mind around things that are kind of difficult to visualize directly. So for example, I can ask you, what are all of the edge midpoints of our cube? Okay, say we want to make a new vertex in the center of each of the edges. What does that configuration look like? Well, we can really get a handle on this very easily using our coordinate. What about the point here in the center of this edge? We know that moving along this edge is the same as changing this first entry of the coordinates from -1 to 1. And so when we do such a change, but we only go halfway, well, we're going to be basically taking the average of these 2 3-dimensional numbers here. And so this edge midpoint has coordinates 0, -1, -1. So this is really remarkable because this pattern extends in all sorts of ways. So for example, so now we know that our vertices have coordinates where each entry is a -1 or a 1. And then if we take such a thing and we turn one of the entries into a 0, we're going to be describing the edge midpoint. And it turns out that we can go further. So what are the coordinates of the point in the center of this square face here, for example? This is a great question. Well, if we're walking around inside this square face, well, you can see that if we start from this vertex here and then we start walking around in this square face here, we can basically do that by varying either the first coordinate or the second coordinate. So it turns out that if we just set those two to be 0, we get this point 0, 0, -1. And that's going to give us the coordinates of the point in the center of this square face of the cube that's nearest to us. Very, very powerful. And so I think you can guess what's going to come next. We can just apply the same idea in 4-dimensional space. And so here's what it looks like. So we can describe a point in 4-dimensional space with 4 numbers now. It has a x, y, and z coordinates, as we are familiar with, but then there's this other kind of mysterious 4th coordinate, which is telling us how far we have to go in the 4th direction to get to our point. Now, in some cases, you might want to imagine that this 4th number is time, or it could be some other physical quantity like temperature, for example. But once again, you can see that we can lay things out here so that the vertices of our hypercube have these special coordinates with all of the entries as -1s or 1s. So for example, if you wanted to confine your attention here to this 3-dimensional cell within our 4-dimensional hypercube, well then your 4th coordinate would be held fixed as -1. And if you change this -1 to a 1, in other words, if you move 2 steps in the 4th direction, then you'd be moving from this cell here to this cell here. But while you're in this cell here and you're keeping your 4th coordinate fixed, basically everything looks just like it did in the 3-dimensional case. And so this gives us some really powerful methods to gain deep understanding of the structure of this tesseract. So this tesseract is a 4-dimensional polytope, okay? So I want to introduce a little bit of language now. So clearly this polytope has vertices, edges, and then 2-dimensional faces, and also these cells. And so when I speak about k-dimensional faces, basically I just mean the sort of k-dimensional bits. So I may refer to these vertices as 0-dimensional faces. When I talk about 1-dimensional faces, I'm talking about edges. When I'm talking about 2-dimensional faces, I'm talking about faces, okay? And then 3-dimensional faces here would be these cells. And sometimes I'll just talk about faces without any kind of qualification, and then you should assume I'm talking about the 2-dimensional case. Anyway, a really, really great question is, what are the 2-dimensional faces of the tesseract? So for example, what are the coordinates of the center of this 2-dimensional face here with these green and blue edges? And we can get the answer just as before. We know that we're talking about a 2-dimensional face, so we know we should be setting 2 of the coordinates to be 0. Which 2 coordinates should we pick? Well, if we start here and we want to walk around in this square, you know that we're either going to the right or we're going up. So those correspond to our first 2 coordinates. So if we set those to 0 to represent that we've gone halfway in both of those directions, well, we'll keep the other 2 coordinates to be -1, -1. And you can see that we've now got the coordinates for the center of this 2-dimensional face of our tesseract in 4D space. And if you like combinatorics, you can probably figure things out now, like how many 2-dimensional faces does a tesseract have? Basically, it's the number of ways that you could have 4 numbers, 2 of which are 0, and the other 2 can be either 1 or -1. So there we are. We're making some really good progress now. So let's just recap. We want to understand what all of the regular polytopes are. We've understood what's going on in 2 dimensions. There we've just got our regular polygons. We've understood the case with 3 dimensions. There we've got our 5 Platonic solids. And now we've just found the infinite family of regular polytopes, these hypercubes. And you can see with this pattern here, we can go all the way from the 0-dimensional hypercube, that's just a point, all the way up in dimensions, okay? The line, the square, the cube, the tesseract, the 5-dimensional hypercube, the 6-dimensional hypercube, we found an infinite family of regular polytopes extending up and up in dimension. So the question that we want to answer is, what are all of the regular polytopes? And it's a surprisingly easy question to answer. In fact, we're almost there. There are just two other kind of infinite families of regular polytopes, and then just a couple of outliers that we need to talk about. And then we'll understand everything. So the next family of shapes I want to talk about are remarkably simple. And so to introduce them, I want to show you one idea. So there's an easy way that you can take a two-dimensional shape, like this square that I've drawn here, and you can use it to build something three-dimensional. Basically, you can use this square as the base of a pyramid. And so when you do that, you end up with a 3D shape like this. So this process is called forming a pyramid. And it's very interesting because you've just created this new vertex here, this sort of apex of your pyramid. And you can choose which point of the base you want that to be above. And you can also choose how high you want it. Now, if you're interested in making symmetric shapes, you might want to select these things in a very special way. Perhaps you want the apex to be above the center of the base, especially chosen height and so on. But I'm just showing you how you can form pyramids, because it turns out that you can do exactly the same kind of thing in higher dimensional space. You see that forming this pyramid here lets us go from a 2D shape to a 3D shape. So what about the same idea in higher dimensions? What about if we have this three-dimensional cube here? Can we form a pyramid and make something that's four-dimensional? Well, the answer is yes. It's pretty easy to do, actually, at least conceptually. We just decide where we want our apex to be above and sort of how high in the fourth direction we want this apex to be. And we're going to get something that looks like this. And so actually we can use this idea of forming pyramids to get our other two infinite families of regular polytopes. So now I want to talk about the simplest kinds of polytopes in spaces of general numbers of dimensions. And these polytopes are called simplexes. Okay, so you know the two-dimensional simplex very well. It's just the equilateral triangle. And the three-dimensional simplex you're probably also very familiar with. It's just the regular tetrahedron, the simplest 3D polyhedron. And it turns out that we can go up and up in dimension and make higher dimensional versions of these simplexes. So how do we do it? Well, it's pretty easy. So for example, if we take our two-dimensional simplex here, our regular triangle, well, basically we can make a three-dimensional simplex just by forming a pyramid. So we take our triangle and then we add a new vertex, which is sort of above our triangle in our new kind of third dimension. And of course, we can set this up so that this triangular base pyramid is regular. And now we have our tetrahedron. This is our three-dimensional simplex. But it turns out that we can carry on, okay? So if we take our tetrahedron and then we add a new point in the fourth dimension that's above this tetrahedron, well, we're going to get this shape here, which is our four-dimensional simplex. This is sometimes called the 5-cell. Why is it called the 5-cell? Well, think about the tetrahedron. So the tetrahedron has four two-dimensional faces. It has these four equilateral triangles. And in a similar kind of way, this four-dimensional simplex has 5 three-dimensional cells. So it's a remarkably interesting form. We're going to see an animation of it shortly. And of course, we can continue this pattern, okay? There's a 5-dimensional regular simplex and a 6-dimensional one and so on. And so these simplexes are very, very important. So basically, when you're in n-dimensional space and you want to make the simplest kind of polytope that you can, you just get n+1 points that are spaced out in a totally symmetric way. And those form the vertices of a regular simplex in n dimensions. So much like how not every triangle is equilateral, of course, not every simplex is regular, but we're really going to be paying a lot of attention to the regular simplexes. So we're almost there. There's just one other infinite family of regular polytopes and then a couple of outliers. The outliers are absolutely fascinating, okay? So we're soon going to get onto those. But it turns out that this last family that we need to describe can also easily be described using this idea of pyramids. So once again, we're going to start off in the two-dimensional case with the square. And the regular polytopes that I want to describe now are called cross polytopes. The two-dimensional cross polytope is easy. The two-dimensional cross polytope is the square. You already understand that. So the last kind of infinite family of regular polytopes there is are called cross polytopes. They're also very easy to understand using this idea of pyramids. this is the two-dimensional cross polytope. You're very familiar with it. It's just the square. Okay, the square, obviously, it's a regular polytope in 2 dimensions. What about in 3 dimensions? Well, you've also met the 3-dimensional cross polytope. It's just the octahedron. Okay, so here it is. And what I'd like you to see here is that we can form the octahedron by getting our square and then making a couple of pyramids. So I think this kind of thing is called a dipyramid. Okay, so we get our square and then we make a pyramid on the top and a pyramid on the bottom, and hey presto, we have our octahedron, which is our 3-dimensional cross polytope. Of course, we select our heights and setup for our pyramids so that everything ends up being regular and symmetric. And this is the only idea we need. We just carry on with this notion. So how do we get our 4-dimensional cross polytope? Well, we get our 3-dimensional cross polytope, and again we form this kind of dipyramid. So we make a pyramid on the top, so we introduce 2 new vertices, and they're going to be linked to everything that we already have. So we basically get our octahedron, which is in 3D, and then we add a new kind of apex at the top, which is above this thing in the 4th dimension, and also one below it in the 4th dimension, and those are going to form a sort of pyramid on the bottom and a pyramid on the top. And so this is our 4-dimensional cross polytope, and this pattern continues on with higher dimensions. So to make a 5-dimensional cross polytope, we just get this one here, and then we add a couple of new points in the 5th dimension, and so on. Now, because I'm drawing these edges and so on, I talk about, oh, I have to link this vertex to this other vertex, but it turns out that you can really do this whole thing just in terms of describing the coordinates of your vertices. And if you do this, for example, in a computer, you don't really need to worry about thinking about what's going to be linked to what, because you're forming this kind of regular polytope. So if you just know the coordinates of all of the vertices, then you can just calculate the minimum distance between a pair of distinct vertices, and then you know that any 2 vertices spaced by that distance are going to be linked. So hopefully you're gaining some intuition now for these polytopes. And we're almost done with our classification now. We've almost seen all of the regular polytopes. In fact, there's just 3 left, okay? So it turns out that if we look in a space of any number of dimensions and we look at all the possibilities, it turns out that out of all of the number of dimensions and all of the possibilities, there's actually only 3 shapes left. There's only 3 regular polytopes that we haven't seen yet. And they all live in 4-dimensional space, and they all have absolutely extraordinary features. We're going to see them very shortly. But just before I want to introduce them, I want to tell you about some other ideas that are really going to help us. So I'm deliberately trying to take a kind of intuitive approach towards this stuff and not get bogged down with formalities and definitions. But I want to at least outline what I mean by this phrase regular polytope in a bit more of a concrete way. So a notion that's going to help us here is this idea of what's called a convex set. So if we have some space, let's say for example 2-dimensional space, then we can speak of a subset of that space, you know, a set of points inside that space. And we can ask, is that subset convex? Now, what do we mean by that? Well, the definition of a convex set is that if we pick any pair of points inside that set, and then we draw the interval, the line interval between those 2 points, that line interval is completely contained within that set. And this should be the case no matter which 2 points we pick. So you can see that this disk here is a convex subset of our space, whereas this crescent moon shape here is not convex, okay? Because I can pick a point up here and a point down here, and then if I draw the line between them, you can see that that's not contained within the set. So of course some people think about shapes in higher dimensional spaces that are not convex, but we're really going to restrict our attention to these convex shapes. So we're always talking about convex polytopes. So whenever I talk about a polytope, I mean a convex polytope, and since I'm using this convention, I can really tell you what I mean by the word polytope in terms of convexity. So if you pick a set of points in your space, for example, in 3D space, I might pick these 3 points here. That might be my set. Well, then you can form something called the convex hull of that set. And what that is it's the smallest convex set that you can make, which contains those points. This is another really powerful idea because the convex hull of these 3 points here is this triangle here with the interior filled in. And that's a polygon, okay? That's a 2-dimensional polytope polytope. And so for the purposes of this video, we can define a polytope to be, in general, something that you can get by taking a finite set of points in n-dimensional space and then taking the convex hull of that set of points. And that's going to result in a polytope with all of its vertices and edges and k-dimensional faces and so on. So in a sense, that's why knowing where the vertices are of a regular polytope is enough, because the regular polytope is just the convex hull of its set of vertices. So what do I mean when I use this word regular? Well, I don't want to be too rigorous here. Basically, let me just say that a regular polytope has the feature that for any k, if we have a look at any two k-dimensional faces, those are basically going to look the same as each other in the sense that there's a kind of symmetry, you know, like a rotation or a reflection or something that sends one of these elements to the other one. So every vertex looks like every other vertex, every edge looks like every other edge, every 2D face looks like every other 2D face, and so on. That's the feature that defines regular polytopes. So there's one other idea that's going to be really useful for us in developing language to talk about these higher dimensional shapes, and it's really a kind of similar idea to the notion of a convex set, and it's called an affine set. So if we have some space, like n-dimensional space, again, we can pick a kind of subset of that space, and we can ask, is this affine? And what do we mean by that? Well, basically, this set is going to be affine when, if we pick any pair of points within the space, then the infinite line that we can draw that goes through those points has to be contained within the space for it to be affine. So even though this disk here is a convex set, it's not an affine set because, you know, okay, we can pick these 2 points and the line segment between them is contained within our disk, but now we want to be considering this kind of line extended infinitely, and you can see that that's obviously not totally contained within our disk. So our disk is not an affine subset of 2-dimensional space. So let's have a look at a positive example then. Now think about this cube here in 3-dimensional space. Well, we can see that this cube has faces. This is one of the faces of a cube, so this is going to be a square. This is a convex subset of 3D space, but it's not affine, of course. We can draw this sort of infinite line through these 2 vertices, and that line's not entirely contained within this face because this face is just a finite region. But you can see that we can extend this face out to be the kind of plane that sits on top of our cube, okay? So imagine you have a cube and then you place a kind of infinite plane resting on the top of it. That plane is a sort of 2-dimensional subset of our 3-dimensional space, and it goes on forever, and it's affine, right? Because if we take any 2 points within this purple plane and we draw the kind of infinite line through them, that line is entirely contained within that purple plane, that kind of affine subset of 2-dimensional space. So much like with the convex case, we can define this notion of the affine hull of a set of points. So if you take a set of points, for example, these 4 vertices here in 3-dimensional space, well, then you can form the smallest affine set that contains those. And that's sometimes called the affine hull of those points. And that's going to be this 2-dimensional plane that I'm talking about. So you see here that we have this 2-dimensional affine subset of our 3-dimensional space. We call that kind of thing a flat. So a k-dimensional flat is just a k-dimensional affine subspace. And you can see that these flats get generated by our k-dimensional faces in our polytope. So for example, if you pick a 1-dimensional face of your polytope, in other words, if you pick an edge, well, that's going to be convex, but it doesn't go on forever. But we can extend that, and now we have this infinite line, and you can see that that's going to be a 1-dimensional flat, okay, because it's 1-dimensional and it extends infinitely in every appropriate direction. And similarly, we can extend these 2-dimensional faces by taking their affine hulls, and then we get these 2-dimensional flats and so on. So this is a very interesting kind of mind-bending idea, okay, because for example, suppose we're in 4 dimensions now, and we can concentrate on one of these 3-dimensional cells here of our polytope, one of these 3-dimensional faces. So that's going to be this convex set, but we can also think about the affine hull of that. And this is a bit weird, okay, because what we end up getting then is this kind of 3-dimensional space which goes on forever. And so we can look at one of the 8 cells of our tesseract, for example, and consider the flats that it generates. And that's going to be this 3-dimensional space goes goes on forever in each of the three directions, but it does not constitute our whole space, okay? Because our whole space is four-dimensional. So this is a very interesting kind of mind-expanding thing to think about. And one other little piece of terminology I'll introduce while we're talking about this is the idea of a hyperplane. So when we're in n-dimensional space, a hyperplane is just an n-1 dimensional flat. So when we're in two dimensions, the hyperplanes are just these lines that go on forever. When we're in three dimensions, hyperplane is just a plane. Okay, so like this, for example. And the pattern carries on. Okay, so when we're in four dimensions, a hyperplane is a three-dimensional flat, which, for example, could be one of these so-called bounding hyperplanes, which is formed by taking the affine hull of one of the n-1 dimensional faces of our polytope. So I think some people use this term hyperplane to mean the same thing as flat, but I'm going to try and only use the word hyperplane to refer to the n-1 dimensional flats in this case. Okay, so now I want to tell you about some notation, which is going to let us describe these regular polytopes very, very concisely. These are called Schläfli symbols, and they let us describe regular polytopes exactly. And there's also some wonderful kind of coincidences about how these Schläfli symbols interface with Coxeter groups that we're going to talk about later. So what are Schläfli symbols? Well, let's start in the two-dimensional case, okay, where we have regular polygons. In that case, if we have a regular polygon with p sides, then the Schläfli symbol for that polytope looks like this in curly brackets. So the Schläfli symbol for an equilateral triangle is just a 3 in curly brackets. Okay, so that's the case in two dimensions. So let's carry on. What about the three-dimensional case? So let's suppose we have now a three-dimensional regular polytope. For example, it could be a cube. Well, in this case, there's going to be a Schläfli symbol for that. And here is the Schläfli symbol for the cube. Now, the reason that the cube has a Schläfli symbol 4, 3 is that the cube is made out of fourgons. So this first number here is describing how many edges the polygons have that are forming the faces of our polyhedron. And then this second number here is telling us how many of those faces meet at every vertex. So in a cube, you can see that it's made out of fourgons. That's why this is a 4. And we have 3 of these meeting at every vertex. That's why this number here is a 3. And so more generally, if we write this Schläfli symbol P, Q, well, this is going to be referring to a regular polyhedron, something that has pgons for faces, and we have Q of those faces meeting at every vertex. So if you like, you could say that P, Q is a three-dimensional regular polytope that have faces which are P's, because this P in curly brackets refers to a pgon. So you can sort of unpack this in chunks. If you have a look at this, you can see the first bit is a P, and then this is telling you that there's going to be Q of them touching every vertex. Or another way you could say it is every vertex has Q edges which are touching it. So you can see here that the Schläfli symbol for the icosahedron is 3, 5. Because the faces are three-gons or triangles, and you can see that we have 5 of them touching every vertex. This case is also interesting with the tetrahedron or three-dimensional simplex, because its faces are three-gons and we have 3 of them touching every vertex. So a really great thing about these Schläfli symbols is that they can also be used to easily describe these regular polytopes in higher dimensional space. So this is the Schläfli symbol now for this tesseract, this 4-dimensional hypercube. And the first 2 numbers in this Schläfli symbol are telling us about the forms of the cells, the 3-dimensional faces of this thing. Okay, so I've told you that the tesseract has these 8 cells, which are 3-dimensional cubes. And the Schläfli symbol for a cube is 4, 3. And so the first 2 numbers that we have here are literally just giving us the Schläfli symbols for the cells in our regular polytope. And what about this last number? What's this telling us? Well, this is telling us how many of those cells there are touching any particular edge. Okay, so if we pick any edge in this case of our tesseract, we can see that there are going to be 3 of these cells which are touching it. In this case, there's going to be this 3-dimensional cell here, this 3-dimensional cell here, and also this one here in the middle. And it's remarkable that this kind of information is enough to understand the form of our regular polytope. So I've spelled things out properly here. For a regular polygon with p sides, this is its Schläfli symbol. If we have a polyhedron, something in 3-dimensional space, with a Schläfli symbol P, Q, that means it has faces that look like this, and there's going to be Q of them touching every vertex. This is the case for the regular four-dimensional polytopes. So this Schläfli symbol here means that the cells, or the three-dimensional faces, are going to have a Schläfli symbol P, Q, and there's going to be R of them placed around every edge in this regular polytope. And so it turns out that we can use these Schläfli symbols to describe what's going on even at higher dimensions. So this is the general case for a p-dimensional polytope, but I'm not going to dwell on this. I'm just going to move on. You can pause the video and look at this, or you can look at Schläfli symbols on Wikipedia if you want to understand more. What I want to take a look at now is this beautiful table here, because in looking at this, we can finish understanding all of the regular polytopes. So let's recap. We have the two-dimensional regular polygons. We have the 5 Platonic solids in 3 dimensions. And we have these 3 infinite families which we discovered, the hypercubes, the simplexes, and the cross polytopes. And it turns out that these are all the regular polytopes except for 3 cases. And those missing 3 cases, those exceptional things, they all live in 4-dimensional space, and they are described by the last 3 rows here of this table. So aspects of this table might seem mysterious to you still, but you can see here that we have these Schläfli symbols, so we can use these if we like to understand what these final 3 regular polytopes are. They're called the 24 cell, the 120 cell, and the 600 cell, and they're all absolutely beautiful. So of course we're going to take a more direct look at these, and at some point we're going to understand what these Coxeter diagrams mean. And believe me when I say that once we understand about these Coxeter diagrams, we're going to achieve a whole new level of understanding of these regular polytopes. In fact, we're going to understand all of the symmetries of all of these shapes simultaneously in a totally visual way. It's going to be so good. But let's just go step by step, okay? Because there's a lot of information coming here. What about this first row here? What is this talking about? Well, this is talking about our 4-dimensional simplex. This is our 5 cell. We've already seen it. And this information here is telling us how many 3-dimensional, 2-dimensional, 1-dimensional, and 0-dimensional faces there are. So, the 5 cell has 5 3-dimensional faces, hence the name. We can also see that the Schläfli symbol for those cells is 3,3. What this is telling us is that the 3-dimensional cells in this 4-dimensional simplex are tetrahedra, because the tetrahedron has Schläfli symbol 3,3. Actually, we can easily see this directly because the first 2 numbers in the Schläfli symbol are both 3s. Now, here is something else very interesting. It says dual here, okay? So did you know that duality not only works in 3 dimensions, it works in spaces of any number of dimensions. So we saw earlier on that if we have a regular polyhedron, like for example a cube, and then we place a vertex in the center of each of its 2-dimensional faces, then we get another regular polyhedron, the dual, in this case the octahedron. Well, it turns out that you could always do a kind of analogous thing. So in general, if you have a polytope in n dimensions and you want to dualize it, all you do is you look at all of the n-1 dimensional faces and you place a vertex in the center of each of those, and those new vertices that you've placed down form the vertices of the dual of your original polytope. This is extremely beautiful. So now we can ask, for example, for this 2-dimensional regular polytope here, this square, we can ask, what is the dual of this? Well, we just look at all of the 1-dimensional faces and we place a vertex in the center of each of those, and those are the vertices of our dual. So we find that in 2 dimensions, the dual of a square is just another square. In this case, it's kind of rotated a bit. We can also, much more interestingly, apply the same idea in 4 dimensions, okay? So we can ask, what is the dual of this tesseract? Well, to determine the dual of the tesseract, we just look at all of the 3-dimensional faces and we just put a vertex in the middle of each 3-dimensional face. And so there are 8 of these 3-dimensional faces, and it turns out that when we place a vertex in the center of each of them, those form the 8 vertices of, can you guess, the 4-dimensional cross polytope. Okay, so this is absolutely beautiful. We have the dual of the tesseract is this thing called the 16 cell. The 16 cell is what I've been calling the 4-dimensional cross polytope. It's also called the 4-orthoplex. And in fact, this process of dualizing has a very interesting effect on all of these kind of k-dimensional faces. When we dualize, these 3-dimensional faces become vertices, these 2-dimensional faces become edges, and so on. And so if we sort of form a list of the stuff stuff at different dimensions, then we kind of reflect this list about the middle, and the resulting list describes the stuff in the dual. So like the dual of the Tesseract is the 16 cell, and it's no coincidence that to get the Schläfli symbol for the 16 cell, we just get the Schläfli symbol for the cube, and we just reverse the order of the numbers, okay? So just like in 3D, this idea of dualization is really powerful because it essentially halves the amount of work we have to do. But that's fine, because if you want to understand cross polytopes, you could really just study hypercubes and then exploit this kind of duality. So that's a little bit about duality. Now here's another very interesting question. Say you have a simplex in n dimensions. Now, what is its dual? Now it turns out that when you have a simplex, like usually when you dualize something, because you know the dual of the dual is the original thing, you have to preserve information. And because the n-dimensional simplex is really the kind of simplest shape in n-dimensional space, it's kind of forced that the dual of that has to be basically just another n-dimensional simplex. And we already saw this before with the tetrahedron, for example. So the same kind of pattern works in general. The dual of an n-dimensional simplex is the n-dimensional simplex. So with that being said, we're finally in a position to understand the final 3 regular polytopes. And here they are. So you have the statistics about these things here. You also have the Schläfli symbols. So we can use these to gain some understanding of what these polytopes look like, but we're going to go much deeper into this. So let's start out with this 120 cell here. And basically a 120 cell, we're going to look at a video of one in a minute, but basically a 120 cell is the sort of 4-dimensional analog of a dodecahedron. It's an extraordinarily beautiful and rich object. Of course, it's highly symmetric. It has 120 dodecahedra as its 3-dimensional cells, hence the name. And we can see that because the first 2 numbers here in the Schläfli symbol are 5, 3, and that's the Schläfli symbol for a dodecahedron, being made out of pentagons, 3 of which meet at a vertex. And then it turns out that much like how in 3D, the icosahedron is the dual of the dodecahedron, so also in 4D, there's a dual of the 120 cell, and that's this thing called the 600 cell. And this is the sort of 4-dimensional analog of an icosahedron. It's another remarkably beautiful shape, and it has 600 tetrahedra as its 3-dimensional cells. So is that it? Are we done? No, there's one more, and I've saved the best to last. There's this one here, which is the 24 cell. And I simply think that this is one of the most extraordinary shapes in mathematics. It's absolutely beautiful. It has so much symmetry, and it's a complete one-off. It exists in 4-dimensional space, and there's nothing like it in lower dimensions. You see, pretty much all of the other regular polytopes that appear are basically like kind of higher dimensional analogs of things that we can find in 3D, but not the 24 cell. This is something extraordinary, and it has so much symmetry. It's very beautiful. It's going to be fascinating. We're going to be looking a lot more at the 24 cell later, and it's going to be absolutely fascinating. But just something that I want to draw your attention to here is this, just to show you one of the reasons why the 24 cell is so amazing. Look what the dual of the 24 cell is. It's the 24 cell. Okay, so yes, if we have a simplex, the dual of that simplex is the simplex. In a way, that's a kind of consequence of everything being very simple. But the 24 cell is extraordinary. It's the only regular polytope, apart from your regular polygons and your simplexes, that is its own dual. And this is an absolutely remarkable feature of the 24 cell. And it's related to some kind of symmetries which this thing has, which I think are deeply interwoven into the fabric of reality. So I always travel with this 3D print here, and this is a 3D projection of the 24 cell. It's absolutely beautiful. We're going to understand more about the geometry of this thing later, but at this point I just want to tell you enough to be able to understand exactly what the 24 cell is, and I can do that very succinctly. So we're getting very familiar now with the Tesseract, the 4-dimensional hypercube, and it turns out that if you understand the Tesseract, it's very easy to use it to form the 24 cell. All we have to do is look at the 2-dimensional faces in this Tesseract and just look at the centers of those two-dimensional faces. And there's actually 24 of those, and we can think of those as the 24 vertices of this 24 cell. Okay, so just look at all of the 2D faces here, and we can just draw a point in the middle of each of those, and then those points that we're drawing down, they're actually going to be the vertices of our 24 cell. So that's a really easy way that you can start to understand the structure of this beauty. I mean, you may ask, what about the edges and so on? Well, I mean, basically the edges are going to be of this kind of form. For example, these two things are going to be linked by an edge because this 2D face here and this 2D face here interface at an edge in the tesseract. And don't worry too much about that. In fact, you don't need to understand the 24 cell very well at all at this point. We're going to come back to it and have a sort of deep dive and really understand more about this beautiful structure. But let me just quickly say that we've already talked about how we can use coordinates to refer to the things in this tesseract. So if you remember, if we have 4 numbers and each of those numbers is -1 or 1, then we can think of those 4 numbers as giving us the coordinates of one of the vertices of our tesseract. And we also saw that we can refer to the centers of the two-dimensional faces with 4 tuples of numbers like this, for example, 1, -1, 0, 0. Okay, so we have 2 zeros because we're talking about the center of a two-dimensional face in our 4-dimensional hypercube. And so it turns out that 4 tuples like this, where 2 of the numbers are 0 and the other 2 numbers could be 1 or -1, those actually give us the coordinates for the vertices of the 24 cell. And you could think of this as a consequence of the fact that we could think of the 24 cell really as having vertices which correspond to the centers of the two-dimensional faces in the tesseract. Okay, so we're really just scratching the surface here of the beautiful goings-on that happen behind this 24 cell. You see, there's actually something else going on here, which is some kind of a so-called triality or a sort of threefold symmetry, something that we're maybe not very used to, but it's very, very important. So to understand more about this, I'd like to direct your attention back to this case here in 3 dimensions, because basically there's something analogous that's happening for the 24 cells. So remember that if we have a cube, the dual of that cube is this octahedron here. And remember that when we make these things the same size, they kind of interpenetrate each other at these special 12 points that form the vertices of our Cuboctahedron here. And so basically pretty much the same thing happens in 4 dimensions, except instead of getting a Cuboctahedron, we get a regular polytope. We get our 24 cell. So there's several ways of describing what a 24 cell is. Another way you can describe it is as follows. Get a 4-dimensional cross polytope and take the center of each of its edges and mark that as your point. And then you're going to get 24 points, and those 24 points are the vertices of your 24 cell. Well, basically, that's pretty much the same thing as what we're seeing here in 3 dimensions with our octahedron. That's a 3-dimensional cross polytope, except that, for the 24 cell, we pumped up the dimension of everything by 1. So what I'm basically saying here is that, yes, if you have a 4-dimensional cross polytope, you can look at the centers of each of its edges, and they're going to be the 24 vertices of your 24 cell. But it's actually more beautiful than that, because the cross polytope and the tesseract are actually duals to each other. And so you can form a sort of compound, an analog of this kind of thing, in 4 dimensions. And then you can see that where the centers of the edges of the cross polytope go through your tesseract, well, they're going to go through the tesseract at the centers of the 2-dimensional faces of the tesseract. And we've seen that those also form the 24 cell. Well, they better do, right? Because we're talking about the 24 cell in 2 different ways. And now we're thinking of its vertices as these special places where the kind of edges of our 4-dimensional cross polytope go through the 2-dimensional faces of our tesseract. But it's even more beautiful than that, okay? So far we've got some kind of a compound of a tesseract and a 4-dimensional cross polytope. But it turns out that actually if we look at that tesseract, that's a 4-dimensional hypercube, right? And maybe you remember earlier on, I was talking about this notion of a demicube. So it turns out that in general, if you have an n-dimensional hypercube, then you can form this structure called a demicube. Basically, you highlight a vertex of your hypercube, and then you don't highlight the neighboring vertices that are linked to it by a single edge, but you do highlight the neighbors of those. So you highlight the things that you can get to from 2 hops and so on. And so you sort of pick every other vertex of your hypercube, and that's called a demicube. So what do you think you get as this kind of of four-dimensional demicube, what do you get if you pick every other vertex of a tesseract? You get a four-dimensional cross polytope, okay? This is beautiful. If you have a four-dimensional hypercube and then you pick every other vertex, you get a four-dimensional cross polytope. So this thing here splits into two four-dimensional cross polytopes. And so we have three four-dimensional cross polytopes that our sort of compound consists of. And the way that those interface with each other to give us the vertices of the 24 cell is absolutely beautiful. It has to do with this thing called triality. And I believe that it's going to end up being extremely important for fundamental physics. I kind of feel like there isn't enough appreciation for the 24 cell. I'm only actually scratching the surface of this. It's much deeper. Anyway, so here we are, we're done. So it's remarkable that now we've actually found all of the regular polytopes, okay? There are no more in any dimension. So, okay, let's recap. We've got our regular polygons in 2 dimensions. We've got our Platonic solids in 3 dimensions. And then we've got these 3 infinite families, the hypercubes, the cross polytopes, and the simplexes. And in addition to those, we have these 3 things here. And these are all in 4 dimensions, the 24 cell, the 120 cell, and the 600 cell. So to reward ourselves for all that hard work, let's have a look at some animations of these things. So I got these animations from Wikipedia. This one here is for the Tesseract. So we're looking at the kind of 3-dimensional shadow of this, and it goes through this kind of breathing motion as this thing rotates in 4 dimensions. You can see that the kind of inside and the outside are swapping their places. This is really an artifact of the way that we're viewing this, because we have to sort of project it down to something that's 3-dimensional to get a picture of it. Here's the next one here. This is the 5 cell. This is the 4-dimensional simplex. You can see that you can make a model of this by getting a tetrahedron in 3 dimensions and then adding a new point that's linked to all the things that we already have. So it has these 5 tetrahedra as its 3-dimensional cells. This is our 4-dimensional cross polytope. This is the jewel of the tesseract. This is this beautiful 120 cell. It has 120 dodecahedron shaped cells. This is a projection of the 120 cell down to 3-dimensional space. So the 120 cell is the kind of 4-dimensional analog of the dodecahedron. And here's the jewel of our 120 cell. This is the 600 cell, 600 tetrahedron shaped cells here. And of course, I've saved the best for last. This is the 24 cell. It's not so easy to see from this animation. We're going to look at lots of visualizations of this thing later. But the 24 cell has 24 cells and they are octahedra. So because this is self-dual, the number of cells it has is the same as the number of vertices it has. That's 24. And we can see here that the Schläfli symbol for the 24 cell is 3,4,3. That's because the cells are octahedra and there's 3 of them touching every edge. And so that's it. We're done. Those are all of the regular polytopes. Isn't it amazing that these are the only ones? Why isn't there a regular polytope in 5 dimensions that's like an analog of the dodecahedron? What's going on with the 24 cell? So many mysteries which really seem deeply interwoven with the fabric of reality. My prediction is that as theoretical physics goes on, there's going to be more and more connections with this theory of regular polytope, because these things are the most symmetric kind of finite shapes that there are. So I'm just showing some information here about the Schläfli symbols of the simplex, hypercube, and cross polytope in general. I'm not going to go through this, but you might want to pause the video and take some time to think about how these Schläfli symbols work at higher dimensions. The next part of this video is the most fun, okay? We're going to understand all of the symmetries of all of these things, and it's going to be so easy. You're not going to believe it. Okay, so here it is, the big payoff. Why do we care about these regular polytopes? Well, there's lots of reasons, but one of them is because they're so beautiful and symmetric. But what good is that if we can't understand what symmetries they have? Well, if you've ever studied the symmetries of a square, you might be a bit dismayed about how kind of difficult it is if you have to draw out some giant table and spend ages thinking about, oh, you know, if I combine this symmetry with that symmetry, I get the other symmetry. And I think that a lot of mathematicians get get so bogged down with algebra, but we're going to see within the next 5 minutes how we should be thinking about symmetry. This is absolutely beautiful. Okay, so I'm just going to dive straight into this and explain it with a geometric example, the triangle. But what I'm saying here applies in exactly the same way for every one of the regular polytopes that I've talked about, no matter if it's in 4 dimensions or 4,000 dimensions. This is the method that you can use to understand all of the symmetries. So what is the method? Well, we start by getting our regular polytope. In this case, we're working in 2 dimensions, and our regular polytope is this equilateral triangle. And we want to understand its symmetries. So what do I mean by its symmetries? I mean the different ways that you can do rotations or reflections and leave this triangle looking how it was to begin with. So some of you might know what kinds of symmetries this triangle has. So anyway, let's see this method, which was advocated by Coxeter. Coxeter was a very famous geometer, and it seems to me that he had something of an obsession with mirrors and kaleidoscopes, because he found that if you use kaleidoscopes and they're higher dimensional analogs, you just get all of the symmetries of things like that. In fact, it's just the tip of the iceberg. What we're going to see here is very, very deep. Okay, we start with our regular polytope in n dimensions. In this case, n is 2, and we're looking at this equilateral triangle. So what do we do? Step 1, pick a vertex, and we're going to call that vertex O0. 0 because it's 0 dimensional. Okay, so far so good. What's the next step? Well, the next thing we want to do is to pick an edge that vertex is touching, and we're going to mark the center of that edge with another one of these special points. So now we have 2 special points, O0 and O1, and all we're going to do is carry on. So now we pick a 2-dimensional face that's touching that edge, and we mark the center of that. We call that point O2. And if we're working in a higher dimensional polytope, we just carry on with this kind of pattern. We'd find a 3-dimensional face that 2-dimensional face is a boundary of, and we'd mark the center of that as O3, and so on. Now, because here we're just working in a 2-dimensional case, we can stop, okay? And we now actually have all the points that we need to understand all the symmetries of this thing. So how do we do it? You can see that we found these special points. We found O0, O1, O2, and so on. In general, we'd be going all the way up to ON if we're working in n-dimensional space, and that would be the point in the very center of our polytope. So I'm going to refer to these points as special points, and ON, I'm going to call that the inner special point. The other ones, I'm going to call those outer special points. So O0, O1, etc., they're going to be the outer special points because they're not right in the middle of our polytope. So here's the thing, okay? In this case, we have these 3 points. So what do we get if we have 3 points? We get a triangle. So you can see that we have this big equilateral triangle, but we can also form this sort of smaller triangle that has vertices O0, O1, and O2. So I'm going to do that. So I'm forming this triangle here. Okay, I drew my lines a little bit too long. I hope you don't mind. But really what I want to be referring to here is this region here at the bottom far right. So you can see that this is an irregular triangle. Now, more generally, if we're working with some n-dimensional polytope, this is going to be a simplex. We're going to have n plus 1 special points, and that's going to give us a simplex, probably an irregular simplex. And you can see that this is forming a sort of chunk of our whole regular polytope. We've got a whole regular polytope, and then we've got this piece of it that we've selected, which is this kind of irregular simplex. Now, here's the absolutely beautiful step. What we do is we think about these red and blue lines that we've just drawn as mirrors. So imagine that these are mirrors. So we actually make a physical model, and we place a sort of red mirror and a blue mirror, and that's all we have to do, okay? Then the magic of kaleidoscopes is going to fill this system out, and it's going to tell us everything about the symmetries. It's truly extraordinary. So if we're working with a general polytope, what we do is as follows. For each of these outer special points, okay, so for each O0, O1, all the way up to ON minus 1, we look at those points, and then since these are forming the vertices of a simplex, if we pick any one of these special outer points, for example, O0, well, we can give that a color, okay? So let's give that point a color, in this case, red. And then what we can do is we can look at the kind of n-1 dimensional hyperplane of this simplex that's kind of opposite O0, because that's going to be well defined, right? Simplexes always have this special property that if we pick any vertex, there's going to be a sort of well-defined n-1 dimensional hyperplane that's opposite it within the simplex. And in this case, this gives us this red line here. So I'm going to call such a thing a wall. So for every one of our special outer points, there's going to be a sort of corresponding wall, which is the thing that's opposite that within this simplex. And all we do is we think of those walls as mirrors. And that's all we have to do, okay? And then basically the magic of kaleidoscope is going to teach us everything we need to know about the symmetries of our polytope. So let's have a look exactly how this works. So firstly, let me illustrate what I mean by mirrors. So this sort of region here that we have at the bottom far right, we're going to call that the fundamental region, because we're really going to use our mirrors to reflect stuff from that region around the rest of the shape. And so this is really the fundamental part, and then we're going to look at some images. So if we have a point, an orange point here in this region, well, we can reflect that in our blue mirror and we end up getting this. Or we could reflect it in our red mirror and we can get this. But if you've ever played with kaleidoscopes before, if you've ever got two mirrors and put them like this, or if you've ever been in an elevator with a mirror in front of you and a mirror behind you, you'll know that the reflection of a mirror also acts like a mirror, a kind of virtual mirror. So what we can also do is we can reflect the red line in the blue line, and that gives us this line here. And now maybe, just maybe, you can see what is happening here. You see, we started off with this fundamental region here at the bottom right, and now look, we've just cut up our triangle into different regions, and each region looks like our fundamental region. And how many regions are there? Count them. There are 6. And how many symmetries do you think this triangle has? 6. This idea works in general to give you all the symmetries of every regular polytope. So let's try and understand what's going on here. Basically, what I'm saying is that if you have this red mirror and this blue mirror, you can just keep reflecting stuff and you'll end up being able to get stuff in any one of these 6 chambers. So we've just got this orange point at the top here. So if we reflect this bottom orange point in the red mirror, we get this. And then if we reflect again in the blue mirror, we get this. If we reflect again in the red mirror, we get this. Extraordinary. We're forming this kind of kaleidoscope and we're being able to refer to each of these chambers. But it's much more beautiful than this. So what happens if we move our original point? You can see that all of these other points are moving with it. And so one thing we could do, for example, is move this orange point towards O0. And this is where we notice something else that's absolutely beautiful. You could actually use this notion of symmetry to construct your polytope. If all you know about is this fundamental region here, and you know about these mirrors, and you know about the angles and things, you just know about the geometry of this simplex with points O0, O1, and O2, well, you can use that, right? You can use these symmetries. So if you then look what happens to this point O0 under all these reflections, the images of that are going to form all the vertices of your polytope. Okay, so let's recap because there's so much going on here. Basically, what I'm saying is that if you have any regular polytope in any number of dimensions, you can proceed as follows to understand all the symmetries. You pick a vertex, O0. You pick an edge that's touching that vertex. You call the middle of that O1. You pick a face, which is touching that edge. You call the middle of that O2. Go on and on and on, all the way up to ON. Now you've got an n-dimensional irregular simplex. It's going to look like one of these chambers. We call it the fundamental region. Now, for each of these special points, except ON, we look at the wall opposite that point in our simplex. So opposite O0, which is red, there's this red line here. This is a n-1 dimensional hyperplane, right? It's the wall opposite O0 within this simplex. That's why I've given it the same color. So we select these walls. We're basically selecting all of the hyperplanes of this simplex, except the wall which is opposite ON. And we're going to make all of those walls mirrored. And then we say, okay, since we have these mirrored walls, those are basically going to give us symmetries of our polytope, right? Like you can see that this red line here is a line of symmetry of our triangle. You can think of it as corresponding to this sort of reflection operation where we're kind of flipping over this vertex at the top and this vertex at the bottom right. That's one of the symmetries that this triangle has. So once you've done all this, what are you going to end up with? Well, you're going to end up with n hyperplanes. Okay, in this case, we've got 2 of them because we're working in 2-dimensional space. We've got a red one and we've got a blue one. And those have these sort of corresponding reflections, right? We can reflect in the red mirror or we can reflect in the blue mirror. Those give us some symmetries of our regular polytope, but we don't have all of the symmetries yet. Oh no, it's not a problem. Actually, we can just combine these symmetries. We can look at reflections of reflections and so on, and we can combine these basic reflections in different ways, and they're going to give us all of the symmetries of our polytope. And how many symmetries are we going to have? How many elements are there in the symmetry symmetry group of our regular polytope, exactly the same number as the number of chambers that our regular polytope gets sliced up into by these mirrors, and also by the sort of virtual mirrors that we get by reflecting some mirrors in other mirrors, as in, for example, this yellow case. So this is truly extraordinary. And another absolutely amazing thing, if you think about it, is that in a sense, the only thing that really matters here is the shape of this fundamental region. In fact, if you know the angles that these hyperplanes at the bottom far right are meeting each other at, you can reverse engineer everything. You can even reverse engineer the whole polytope itself, because like I was saying earlier, if you only had the bottom right and you had these mirrored sides, you can use the kind of magic of kaleidoscopes to recreate everything. So let me hammer this home because it's so extraordinary. So what I'm saying is that we can get a group structure from this. Now, I haven't given you any formal definitions from group theory, but basically the idea with group theory is we have these operations that we can do where we're moving things around in our shape, and we can compose them to make other symmetry operations. And so what I'm claiming here is that these sort of 6 chambers that our kaleidoscope has given us correspond to the different 6 symmetries of our triangle here, and that this situation generalizes completely. So our bottom far right region, that's what I've been calling the fundamental region. So which group element corresponds to that? Well, that's what you call the identity element. That's the sort of do nothing operation. So one thing that you can do to a triangle and leave it looking exactly the same is nothing. That's also called the identity, or sometimes people write it as 1, or sometimes people call it I for identity. I'm going to call it 1. And so I'm drawing this little picture of an unaltered triangle inside of this fundamental region here to represent that this is the identity operation. And also, just for notational convenience, I'm going to refer to this red mirror here as A and this blue mirror here as B for blue. Okay, so what happens when we reflect stuff in our fundamental region in this mirror A? Well, we're going to get stuff in this region up here. So what would be a good name for this region up here? Well, how about we just call it A? Now, which symmetry operation corresponds to this region A? Well, the symmetry operation we should associate with this region is the operation where we're swapping around this top vertex of our triangle with this bottom right vertex of our triangle. Why? Well, that's what this symmetry A does. Okay, we know that when we use this red mirror, this is exactly what it does. Think about the big picture here. When we reflect things in this mirror A, we're going to swap round O0 with this black vertex at the very top. So, okay, that's this chamber up here. What about down here? Well, it's a similar story. Okay, we're going to reflect in our blue line B, and that's going to get us down here. So we're going to call this chamber at the bottom right B, and we're going to associate it with this operation here where we're swapping around the bottom left and the top vertex of our triangle. So let's just draw this picture of a triangle up here and number the vertices 1, 2, 3 so that we can sort of keep track of what's going on. So what we can do now, if we like, is we can look at this chamber down here and we can reflect it in A. And so that's going to get us up to this chamber up here. So what should we call this? Well, a good name for that is going to be A after B, because we did the B operation first. That got us from here to here. And then we do the A operation. That gets us from here to here. But which symmetry should we associate with this region? Well, we associate it with the symmetry we get by doing the B operation followed by the A operation. So this is how you usually write this kind of thing in group theory. We write this as A circle B. And when we see that circle, we kind of read that circle as meaning after. So we do B and then we do A. And so we call this thing A after B. And what I'm telling you here is that this thing corresponds to this rotation where we rotate our triangle round by 1/3 of a turn counterclockwise. So why is that? Well, we can easily understand this. Okay, so firstly, we want to do the symmetry operation B, which is going to swap around 2 and 3. And then we want to do the operation A, which is going to swap around 1 and 2. So what is the net effect of this? Well, if we start with 3, for example, then the first thing we do is going to send that to 2. And then the second thing we do is going to send that to 1. So the net effect of doing this kind of operation B followed by this kind of operation A is going to send 3 to 1. What about if we start with a 1? Well, our first operation, the B that we do on the inside, doesn't change it. And then the second operation we do, the A, which is here, sends the thing to 2. And so the net effect is going to be to send 1 to 2. And similarly, 2 is going to get sent to 3. And so composing this symmetry with this symmetry gets us this symmetry. And we can carry on. And so what about if we take this chamber up here at the top right, and then we reflect that in our B line? Well, that's going to get us down down to this chamber here, which we can appropriately call B after A. And if we do the math, we compose these two reflections, we see that we get this rotation here. And then what happens when we reflect this chamber down here in this mirror A? Well, we get this chamber here. And this is associated with the group element A after B after A. We could also call it B after A after B. It ends up being the same, but this ends up corresponding to the final member of our symmetry group, which is this final reflection here. So I find this absolutely extraordinary. We're getting the appearance of all of our group elements and their behavior and the numbers of them and everything just coming out completely naturally from a kaleidoscope. And the most beautiful thing is that exactly the same kind of phenomenon happens for any regular polytope. So you might be a bit concerned at this point. You might be thinking, well, I'm not sure how to think about n-1 dimensional hyperplanes or reflecting in 600 dimensional space. Don't worry, it's actually really easy. There's some linear algebra which can allow us to understand this stuff. We're going to see this later. Okay, so this is our birthday cake, all right? This is really magical. We're going to see more examples of this later. This is the kind of thing that you can easily study with examples and physical models and so on. But I want to show you the cherry on top, which is this absolutely beautiful notation that can allow us to record what's really going on here. So this kind of group that we can get is sometimes called a finite reflection group or a Coxeter group, because Coxeter was one of the main people that came up with this. And there's something that kind of goes along with this, which is called a Coxeter diagram. And so the Coxeter diagram associated with this situation is what I'm drawing here. Now we're going to get used to this through some examples, but let me just give you a flavor of what this means. So basically what we have here is a graph. Now, in this case, I've colored the nodes of this graph just basically for convenience to kind of help you understand what's going on, but you don't have to color the nodes. This is just something I'm doing to help you to understand. Another thing we have here is this edge here that I'm labeling with a number 3. So what do these nodes represent? Well, basically these nodes correspond to our mirrors. Okay, so these are going to correspond to these n-1 dimensional hyperplanes that we're using as the sort of reflective walls of our simplex. And what does this number mean? Well, this number is telling us the angle between these hyperplanes. So it turns out that when you're in n-dimensional space and you have two n-1 dimensional hyperplanes meeting each other, it makes sense to think about the angle that they meet. You can see that this is clear in this case. We can speak about the angle that these two lines meet each other at. What is that angle? It's 60 degrees. I'm actually going to work in radians today. So there are 360 degrees in a circle. We can also say there are 2 pi radians in a circle. So this angle here, we could say it's 60 degrees. We could also say that this angle is pi over 3. And so more generally, if you have a Coxeter diagram that looks like this, where the edge between your nodes is labeled with the number p, that indicates that the angle between these hyperplanes is pi divided by p. And in fact, this is the Coxeter diagram you're going to get if you're considering a regular polygon, which has p sides. It would be a similar situation to the case with this triangle, but we'd have more of these two-dimensional chambers. And so when you see these Coxeter diagrams, as you often will in books on regular polytopes and so on, just remember that the nodes correspond to hyperplanes and the numbers on the edges are telling you the angles between those hyperplanes. And all this is really telling you is how you can build this fundamental region here, because once you've built it and once you've set down these mirrors here, you know everything you need to know. Actually, there's a little bit more notation that you sometimes get. You sometimes have it so that people circle one of the nodes. What do they mean by that? Well, basically what they're telling you there is that once you've built this fundamental region, you should look at the images of your vertex of your irregular simplex that's opposite your red hyperplane. So in other words, once you've built this fundamental region, once you've laid down your mirrors and got your kaleidoscope ready, you ought to be looking at the images, in this case of O0, because they're going to give you the vertices of your regular polytope. In other words, if you see something like this, that's telling you about the symmetries, but it's beautiful because when you know the symmetries, you can highlight one of these nodes here, and then it's telling you actually that you can recover your polytope from this. So let me just tell you a couple of extra things that you'll find with these Coxeter diagrams. So there's two sort of conventions that people use basically just to make things look neater. One of them is that if this p here is equal to 2, well, that means the angle between these things is pi over 2. That means these things are perpendicular. And in such a case, people don't even bother drawing the edge. So when you see two nodes that are not linked by an edge in a Coxeter diagram, that's just a kind of shorthand for meaning, well, they should be linked with an edge, which should be labeled with a 2. Basically, this kind of perpendicularity implies a kind of independence, which is well illustrated by having a lack of a connection there, but it's really just a kind of graphical convention. Basically, absence of an edge really is shorthand for an edge, which should be labeled by a 2, because of course there's always going to be an angle between any hyperplane and any other hyperplane. The other thing is that when you have an edge, which you should label by a 3, very often people don't bother writing a 3. Okay, so if this was an edge which was labeled with a 5, that would mean the angle between this and this is pi over 5, and people would write a 5 there. But the number 3 occurs so many times in these Coxeter diagrams that people just adopt this sort of shorthand where they don't bother drawing the number 3. And so now, if we go back to our beautiful table, maybe this column is starting to make a little bit more sense. I expect it's not completely clear yet. It probably will be after our next example. You can see that we have these Coxeter diagrams here, and you can see that some of these edges are not labeled, and that means we should really label them with a 3, but this is some kind of shorthand. And also, for example, this node here is not linked to this node here, so if we're being complete, we should draw all these missing edges and label those by 2, because they basically mean that the angle between the node corresponding to the first hyperplane and the node corresponding to that other hyperplane, the angle between them is pi over 2. They're perpendicular. So, okay, that's a lot of information. Now, let's get visual. Let's have a look at a 3-dimensional example, because I think this is going to clarify a lot. Okay, so I told you that this method of using mirrors can be applied to understand the symmetries of any regular polytope. So far, we just applied it to the case of an equilateral triangle in 2 dimensions. So now I want to have a look at another example. This time, let's have a look at the cube in 3 dimensions. Let's see if we can understand what all the symmetries of a cube are. So the way that we proceed is just like before. So let us proceed to build this kaleidoscope and understand the symmetries of the cube by applying just the same procedure as before. So remember, we begin by selecting any vertex of our regular polytope. We pick any corner of our cube and we call that O0. And then next, we pick any edge which is touching that vertex. We call the center of that O1. Then we pick any 2-dimensional face that touches that edge. We call the center of that O2. Then we pick any 3-dimensional face and we call the center of that O3. And now we're done, okay? Because we're just looking at this 3-dimensional polytope. And so you see we've selected these 4 points, and we could consider these to be the 4 vertices of an irregular 3-dimensional simplex. So in other words, we could think of these as the 4 vertices of a tetrahedron, but not a regular one. So I can link up these points with edges to illustrate what I mean. And I can see that we have this irregular tetrahedron, and this is forming one of our kind of chambers inside the cube. This is our fundamental region. And what we're going to do is we're going to think of the walls of this tetrahedron as being mirrored. And we're going to do the whole kaleidoscope thing again. We're going to see how this ends up cutting the whole cube into different chambers. And it's going to turn out that the number of chambers that we have is going to be the number of elements in the symmetry group of this cube. But I don't want to draw this with these line segments like this. So I'm going to delete those, and we're going to use planes as mirrors, just like we did before. So we have these 4 special points, O0, O1, O2, and O3. And remember, the outer points are O0, O1, and O2. So what we're going to do is we're going to construct the wall opposite each of these special points within this fundamental region, this tetrahedral chamber. Let's start with O0, that's red. And so we can draw a plane through all of the 3 points apart from O0, and that's going to give us the wall that's opposite O0. And so here's that plane, and we're going to color it red because that's the wall which is opposite O0. That's one of our mirrors. And so now we're going to do the same kind of thing for this outer point O1. So the wall opposite O1 is going to go through all of the special points apart from O1. So we're going to draw a plane through O0, O2, and O3, and that should be blue. And now finally, our other special outer point is O2. And so we're going to draw the plane opposite O2. That's the plane through O0, O1, and O3. And that plane should be colored green to correspond with the point O2. So now we're done. And look at this beautiful configuration that we have. You can see that these three planes that we've drawn are cutting out this kind of fundamental region down here at the bottom. And so these three planes, together with the kind of structure of our cube, is defining this irregular simplex here. And the point, just like before, is that we want to think of these planes as mirrors, and we want to use them to start reflecting things around. So I'm not going to do the whole construction because it starts to look confusing in 3D, but the point, once again, is that we're thinking of these walls as mirrors, and we want to create this kind of kaleidoscopic effect where we're seeing mirrors get reflected in other mirrors. And you know, when that happens, we end up with virtual mirrors, which we should also draw. So for example, if we reflect this blue mirror here in this red mirror, then we end up getting this plane here. And this is a new plane that's cutting up our cube even more. And when we see how everything is getting reflected in everything, what we're going to end up doing is cutting up our cube into lots of different regions. How many regions? Well, the answer is actually 48. And guess how many elements there are in the symmetry group of the cube? There's 48. All right, so this method works again. So I'll leave it to you to verify this. But what I would like to do is to gain some deeper understanding of the kind of geometry of this fundamental region. So this again is really important because essentially once we have this fundamental region set up properly and we've got the angles right and so on, everything's going to reflect round, it's going to fill out the cube, and we're going to end up with 47 other kind of images, other chambers that look like this fundamental region. And so one thing that we'd really like to understand here is what angles these different planes are meeting each other at. Because if we understand that, then we can put things in terms of those Coxeter diagrams like before, and it's going to be really, really helpful. For example, we can ask, what is the angle between the red plane here and the blue plane? So I think I can actually try and figure this out in GeoGebra, and you see that the answer here is that they have a 45-degree angle. So 45 degrees is pi over 4. So what I'd like to do now is to construct the Coxeter diagram that corresponds with this kind of nice symmetric setup. So now our Coxeter diagram has these three nodes, and these are corresponding to our three different two-dimensional planes. And then we know that the angle between the red plane and the blue plane is 45 degrees. So 45 degrees, that's an eighth of a turn. That's pi divided by 4 radians. And so since the angle between the red and the blue plane is pi divided by 4, we're going to label this edge linking these two nodes here with a number 4. And so next we'd like to find the angle between the green plane and the blue plane. So let's do that. So if I click on these two planes, we find that the angle between them is 60 degrees. And 60 degrees is pi over 3. So we want to label this connection here with a 3. And then finally, what's the angle between the green plane here and the red plane? Well, the answer there is 90 degrees. Okay, so that's pi over 2 radians. So if we're going to draw this properly, what we actually want to do now is to link these two things up and label this edge here with a 2. But now, if you remember, actually, we have some convention where we don't bother drawing these edges, which should be labeled by a 2, because for some reason to do with convention, we don't bother drawing connections when these things are sort of perpendicular. So we're going to rub out that edge here. And this is the Coxeter diagram, which is describing for us the symmetries of the cube. And so you're going to see something really beautiful in a moment. So get ready. So why is it a good idea to store this kind of information? Well, basically the reason is that if we have this information, then we know all the angles and things. We know that we've got 3 nodes here. So we know that we're working in 3-dimensional space, and we know that these nodes are supposed to correspond to 2-dimensional hyperplanes. And we also know the angles that are supposed to be between these hyperplanes. And that's enough information for us to be able to set down these mirrors. And now the only thing we need to know is, what should we reflect in these mirrors? I started out this construction by taking the cube and saying, okay, we want to work out what the symmetries of the cube are. And I've sort of roughly described how we can do that. We just start reflecting everything in this kaleidoscope. We end up with these 48 chambers, and they correspond to the 48 elements in the symmetry group of the cube. But it's even better than that, because if we just start with this kind of fundamental region here with these mirrored walls, and we have the angles right, which we can get from looking at our Coxeter diagram, we could actually recover our cube. How do we do it? Well, all we need to do is know which part of the fundamental region should be reflected around in this kind of kaleidoscope. And the answer there is that we want to be reflecting around this red vertex, O0 here. And so if we actually have a diagram like this, where we've circled this vertex, this tells us that we're especially interested in the red plane. And more than that, actually, we want to focus on the sort of corresponding vertex. So the vertex that's opposite the red plane in this simplex is O0. And that Coxeter diagram is telling us once you set up this mirror configuration, just start reflecting O0 around in all possible ways. And when you do that, you're going to reflect O0 around, and it's going to have images at each of the 8 places in the cube where vertexes should go. And so really, this is some kind of beautiful notation for describing actually what the cube is. Now, let me show you one more little thing. What's the Schläfli symbol for the cube? Well, the Schläfli symbol for the cube is 4, 3, and that is not a coincidence. And so now take another look at this column here of our table. Does it make more sense now? So what we're seeing here is that there's an absolutely easy way to go from the Schläfli symbol of our regular polytope to the Coxeter diagram that corresponds to that regular polytope. It's totally simple. So for example, in the 3-dimensional case, our regular polytope is going to have a Schläfli symbol like this, PQ. And so all we have to do is just draw the corresponding Coxeter diagram. So it's going to have these 3 nodes here, and then this connection is going to be labeled with a P, and this connection is going to be labeled with a Q, and we want to circle this, and this is a description of our regular polytope. Using the kind of ideas I was just talking about, actually, this is enough to really be able to geometrically construct our regular polytope. How beautiful is this? So what do I mean here? Well, when we look at this, we've got some thinking to do, okay? So the first thing that we think is, well, how many nodes are there? Well, there are 3 nodes. That means we're in 3-dimensional space. And also each of these nodes is going to correspond to a hyperplane, an n-1 dimensional flat, or a 2-dimensional plane in this case. And we also know the angles between these planes, okay? We know that the angle between this one here and this one here should be pi divided by p. We know that the angle between this one here and this one here should be pi divided by q. And we also know that there's secretly a kind of connection like this that should be labeled with a 2. So we know that the angle between this plane and this plane should be pi divided by 2. These should be perpendicular. And so that's enough information for us to be able to put our mirrors down. And then all we have to do is look at how everything gets reflected. Look at what this kind of kaleidoscope with these mirrors set up like this does. In particular, since we circled this vertex here, we want to be looking at the sort of plane that corresponds to this node, and then the kind of vertex opposite that in this simplex that we've just formed almost all of the walls of. And then we want to start reflecting that around. And that's actually going to allow us to recover our regular polytope. And this exact same method extends more generally to all of our regular polytopes. That's why I was making such a big deal about these Schläfli symbols earlier, because basically we just load our Schläfli symbols into this Coxeter diagram notation, and then we're actually able to reconstruct everything that we want. So in particular, if we're looking at these 4-dimensional regular polytopes, then we're going to be looking at Schläfli symbols like this, PQR, and so we want to be looking at Coxeter diagrams of this kind of form now. Now we have these 4 nodes because we're working in 4-dimensional space, and these nodes correspond to 3-dimensional hyperplanes. But again, we know the angles between them. So in principle, we can do everything that we want to do. So I'll say again, you might be a bit uncomfortable thinking about things like angles between hyperplanes and what does it mean to reflect things in hyperplanes. Don't worry, we're going to get to some really concrete linear algebra based ways of thinking about stuff like that shortly. So I've got one more sort of caveat that I want to add to this, because there's a little bit of a subtlety here in the sense that if we just know where these 3 planes are, it kind of doesn't actually help us to know in some sense how to draw draw our cube. Because if you see these three planes, we can think, well, okay, we can see that they're all running into this point O0 here. And that's actually because when we look at the reflections that we can make using these planes, we're really generating a group. And this point O0 is invariant under all these reflections. That's why when you do some symmetry of the cube, like rotating it round or using some kind of mirror symmetry, the center of the cube is always going to remain in the same place. But if all that we have are these planes, then we've sort of defined the symmetry of the cube, but we haven't really said how far away from the center we're actually going to be constructing our stuff. And so what we can do to understand this better is draw a sphere. And so if we draw a sphere of a given radius, for example, we draw a sphere that goes through this point O0, then we can say, okay, we're actually interested in working on this sphere. All right. So if we only want to draw things on this sphere, then we can do that. And we can do that by playing our sort of mirror game here. So perhaps I can illustrate this. If I add this point onto my sphere, I can say reflect it in this blue plane here. And you can see that that's going to give us another point on our sphere. And so this is very interesting because basically, you know, when we're drawing a cube, in a sense, we don't have to worry about all of this three-dimensional space. In a sense, it's fine just to confine our attention to this particular sphere. Instead of our fundamental region being a kind of three-dimensional region, a kind of tetrahedron, now instead we can really think of this as a kind of spherical triangle. So if we draw rays from O3 through our outer points, O2, O1, and O0 here, then that's essentially pushing these points out so that they're on the sphere. And so we can really think of this as giving us these kind of three corresponding points. We could maybe call them O0 dash, O1 dash, and O2 dash. And those would be respective red, blue, and green points that are kind of the same as the things that we've already got, except that we've kind of projected them back out so that they lie on the sphere. So that's going to end up looking like this. And so now you can see that O2 dash, O1 dash, and O0 dash, which is the same as O0, are forming a spherical triangle. You can see it here at the bottom, and I have this point in it that I'm moving around. And this spherical triangle is really representing our fundamental region in a very nice kind of way. And so effectively, we've knocked the dimension of our problem down by one by confining our attention to this sphere. And our n-1 outer special points are forming the vertices of an n-1 dimensional spherical simplex. And this we can really think of as our fundamental region. This is essentially a way that we can reduce the dimensions of everything that we're working with by one. And it's cool to think of things this way because once we've fixed our sphere, or more generally our hypersphere, once we know the radius of that, and once we know the angles between these different planes, well, these different planes are really cutting our sphere. So we're going to end up with these sort of higher dimensional arcs, which are really forming the kind of walls of this spherical simplex. And those walls are kind of mirrored. And then basically this kaleidoscope thing kicks in, and this kind of spherical simplex, in this case, this kind of spherical triangle with vertices O0 dash, O1 dash, O2 dash, basically we have walls all the way around it, which are mirrored. And then we just start reflecting everything. And we're going to end up with this kind of tiling of our sphere. In this case, that's going to cut our sphere into these 48 pieces, each piece corresponding to one of the elements in the symmetry group. So this is a kind of alternative perspective, or an alternative way that you might want to think about these Coxeter diagrams and Coxeter groups. It's kind of up to you if you want to work in the higher dimensional space and look at the kind of dihedral angles between these hyperplanes, or if you'd prefer to sort of reduce things by one dimension and project things down onto a sphere. But I mean, certainly if someone just gives you a Coxeter diagram like this, well, you can take the kind of higher dimensional approach, as I've mostly been talking about. You can draw the planes and so on, and that'll give you the basic geometry of this fundamental region. But then you still have to decide how far away from this kind of ON point where all the planes meet you want to be for when you're actually drawing the stuff on your regular polytope, okay? So it's like in the picture I've just shown you, if you only know the red, the green, and the blue plane, and you don't know anything else, then you're kind of stuck. You also have to look at where all those those planes meet each other, which is going to be O3 in that case, and then you need to know how far away from O3 you want to draw things. And basically making that decision is kind of like, in that case, making the decision of how big you want your cube to be, or what do you want the distance to be from the center of your cube to the vertex of your cube. That would be the radius of the red sphere that you've just seen. So I really hope that you're finding this illuminating, because I think that this kind of information can allow you to construct all of these regular polytopes for yourself. So for example, what if you want to construct a 5-dimensional simplex? Well, the Schläfli symbol for that is going to be 3, 3, 3, 3. And so if we draw the corresponding Coxeter diagram, that's going to look like this. So it's going to have 5 nodes here, and then these nodes are going to be linked, and then we can label these edges here with 3s. Typically, people don't bother drawing these 3s. And then what we want to do is circle this node here. And so this is our Coxeter diagram corresponding to our 5-dimensional simplex. And then you can go ahead and do the same kind of constructions that we've been thinking about earlier. So each of these nodes is going to correspond to a 4-dimensional hyperplane. We know that the angle between this hyperplane and this hyperplane should be pi divided by 3 and so on. So we know all the geometry. And then we see that all these hyperplanes are going to be meeting at this point O5, and we just need to decide how far away from that we want to be, you know, what's going to be the radius of our 5-dimensional simplex. And then we can put a point that far away in our fundamental region opposite this wall. And then we can just reflect everything around in these hyperplanes, kind of activate the kaleidoscope. And it's going to reflect everything around. It's going to put all these vertices around our simplex. And it's going to give us all these chambers and let us understand what the symmetries are as well. So it's really an extremely powerful method. Incidentally, let me ask you, do you know what the symmetry group of the n-dimensional simplex is? Well, when we have an n-dimensional simplex, that means that we have n+1 vertices of our simplex, and they're kind of arranged in the simplest, sort of most symmetric way possible, because regular simplexes are so simple. And it turns out that the symmetry group in that case just corresponds to the symmetric group on n+1 elements. Because if we have n+1 objects on a table, every way that we can permute them and swap them round is going to correspond to a symmetry, where we're sort of doing some kind of symmetry of our simplex and swapping round these n+1 vertices. And so the finite reflection group, or Coxeter group, that we get in this case is just going to correspond to this symmetric group on n+1 elements. So in a nutshell, what I'm trying to say is that this is the Coxeter diagram for a 5-dimensional simplex. So I hope that you're starting to see how powerful these Coxeter groups are, these setups where we're using these mirrors to generate these symmetries. But what I want to show you next is that these gadgets can actually be used to answer some kind of fundamental questions that we might have about reality. So for the next few minutes, I'm going to use a bit of terminology from group theory, which I might not define. So if you don't know much about group theory, some of the things I say might be difficult to understand, but don't worry, I doubt it'll have much impact on your ability to comprehend the rest of the video. So when we have Euclidean space, let's say n-dimensional space, we'll define what we shall call a finite reflection group to be a group of transformations that we can generate using some hyperplanes. So we're going to have some n-1 dimensional hyperplanes within our space. We're going to use those as mirrors. That'll give us certain transformations. And then, like before, we can compose those reflections to get all sorts of other symmetries. And when that kind of thing results in a finite group, well, then we call it a finite reflection group. Another word for the same thing is a spherical Coxeter group. And that's basically because we can think of such a setup in terms of a sort of spherical simplex, which has vertices O0, O1, all the way up to On-1. Those outer special points, roughly speaking, correspond to these vertices of a spherical simplex. And it's kind of spherical because it's sort of like a tessellation of our hypersphere. It's going to be finite, okay? Things are sort of closed up. So I'll talk more about this momentarily, but I just want to kind of step into the land of group theory for a moment, because there's a very kind of elegant way of thinking about what's going on using group theory. And so let's suppose that we have one of these Coxeter diagrams. For example, it might be this one here, but we can imagine a much more general case where we just have a load of nodes and they're linked up, and then we have these numbers on our edges in some sort of a more general way. And so when we have a Coxeter diagram like that, that's going to give us a group. So what does that group look like? Well, basically we think of our nodes as generators. So let's have a look at this example. So this is our Coxeter diagram. Well, we have to do our usual kind of undoing the shorthand that Coxeter uses. So we notice that this node is not linked to this node. So that means that, like, secretly, we should actually have a link between these nodes that should be labeled with a 2. And so this is really the kind of Coxeter diagram that we should be thinking about. And then in the kind of geometric view, each of these nodes here is going to correspond to a sort of mirrored plane. But now we want to sort of shortcut the geometry and go straight to the kind of group structure. So now instead of thinking about it in such geometric terms, what we're going to do is think of each of these nodes here as corresponding to a generator of some group that I'm going to define. And so we have these three kind of generators, S1, S2, and S3, and basically these are corresponding to our different reflection operations. We use these as generators. We look at the different ways that we can compose them together. For example, this is S1 after S2. That's what this notation means. And then we want to impose some equations so that the resulting group that we have is the thing that corresponds to the geometry that we've been thinking about. So what kind of equations do we have to impose? Well, in this case, we've written down the equations here. So let me try to motivate these. This one's perhaps the easiest one to understand. What it's saying is that for each of our SIs, we have the feature that if we do SI after SI, then the result is going to be the identity. Well, why is that? Well, it's because our SI corresponds to doing a reflection in a plane. And if you have this plane and you do a reflection, that's doing a SI. And then if you do SI again, then you do a reflection followed by a reflection. That's equivalent to doing nothing at all. So doing SI after SI gives us the identity. That's the equation that we have here. And that should hold for every SI. So what about this equation here? This is saying that if we do S1 after S2, that's going to give us some kind of an element of our group. And then if we compose that element of our group with itself p times, then we should get an identity. So where the heck does this equation come from? Well, basically this equation just comes from the simple fact that when we compose together two reflections, the result is always a rotation. So this is a really important result in geometry. And so if you haven't encountered this, I strongly urge you to think about this. You can think about it in the case of two-dimensional space, for example. If you're in two-dimensional space and you have a line and you reflect in that line, so for example, it could be this line here, and then you have another line and you reflect in that other line afterwards, well, then you've just done two reflections. And when you do one after the other, when you compose those, the net effect is going to be to rotate everything in your space by an angle which is twice the angle between those two mirrors. Okay, and actually an analogous result to this holds more generally in higher dimensional space. So really what this equation is telling us here is that when we compose together these two reflections here, the result is just to do a sort of rotation of our space. So if the angle between our kind of mirrored hyperplanes is pi over p, then when we do this reflection followed by this reflection, the net effect of that is going to be to rotate our space by twice this angle, pi over p. So what's 2 times pi over p? Well, it's 2 times pi over p. In other words, this is rotating one piece of a full circle. And so when we repeat that p times, then we're going to go full circle, and that's going to result in the identity. That's why we have this equation here. How lovely is that? And so you can see that's where this equation comes from. Similarly, this equation here comes from here, and this equation here comes from here. And so that's how you can go from your Coxeter diagram to your Coxeter group. And basically you can do something totally analogous to this, starting with any Coxeter diagram. Now, whether the group that you end up with is finite and whether it corresponds to the symmetries of some regular polytope as opposed to the symmetries of something with a kind of infinite tiling or maybe even something in hyperbolic space, well, that really has to do with the particular values which are written on the edges of your Coxeter diagram. You know, it's like if you draw a triangle on a sphere, then the sum of the angles might exceed 180 degrees. It's looking at phenomena like that, which is going to tell you whether this kind of reflection group that you get is finite or not. And so with all that being said, let's now apply these Coxeter groups to answer a really fundamental question about reality. And that is, what are all of the finite reflection groups? Okay, so we've already seen that we can get, for example, the group of symmetries of a regular polytope as one of these finite reflection groups. So what if we want to understand all finite reflection groups? Anything we can get by starting in a finite dimensional Euclidean space and using some sort of n-1 dimensional mirrors and reflecting things around and ending up with a finite number of symmetries. What are all the possible ways to do that? Well, it turns out that basically we can answer that question exactly using just the things that we've already discussed. So I grabbed this text from the NLab page on Coxeter groups because I think it explains the situation in a very straightforward way. So if you know some group theory, you might know that you can take two groups and form another group, which is the kind of product of those two groups. And it turns out that when you do the product of two finite reflection groups, you end up getting another finite reflection group. Basically, it's going to have a Coxeter diagram with several different sorts of connected components corresponding to the things that you're producting together. And geometrically, it'll be the symmetry of something like a prism or a rectangle or something, where you have like orthogonal directions with sort of orthogonal symmetries that don't really interact with each other. And so we call finite reflection groups like that reducible reflection groups because we can kind of break them down into these factors, into these more fundamental bits. So what we're really interested in are the irreducible finite reflection groups, the sort of analog of the prime numbers of finite reflection groups. And so they're the irreducible finite reflection groups, and we can characterize all of them. So here's the beautiful answer to this question of what all the different irreducible finite reflection groups are. They're all here, okay? These different Coxeter diagrams describe all the possibilities. And this space of possibilities is really, really interesting because there's some surprises here. There's basically some enormous, highly symmetric structures that you wouldn't expect to appear as an answer to this question of what all the different finite reflection groups are. And basically these enormous, highly symmetric structures that really appear here as some kind of a surprise end up being absolutely fascinating. Particularly, there's this structure called E8 that many people are starting to think might actually describe all of the symmetries of our universe. Looking at this thing might tell us all of the laws of fundamental physics, okay? So these are very, very deep waters. So how are we to take this table here that I'm showing on the left and really think of this as an answer to our question? Well, what we really have here is this list of Coxeter diagrams here. And so we know how to read Coxeter diagrams now, right? We know that we ought to be labeling these unlabeled edges with 3s. And we know that this is really describing some kind of group structure or some kind of a layout of hyperplanes. And so some of the entries in this table are just telling us particular diagrams like this E6 here. And so this E6 here is this Coxeter diagram with 6 nodes, okay? So this is describing some kind of a situation in 6-dimensional space where we've kind of put some mirrors around and we're reflecting them and making some beautiful, highly symmetric configuration. E7 is describing something happening in 7-dimensional space. This H3 here is describing a situation in 3-dimensional space. Actually, you might recognize this, so we should really draw a 3 here. So really, this is the Coxeter diagram for, can you guess which shape? It's the Coxeter diagram for the dodecahedron, okay? So actually, This is the Coxeter diagram here for the icosahedron, okay? And this is the Coxeter diagram for the 600 cell. So we're familiar with some of these. You might also be able to figure out what this one here is. Basically, this is the Coxeter diagram for an m-gon. And so when we're looking at this bottom entry here, we want to be thinking about m as something variable, okay? So amongst this kind of list of different possible irreducible finite reflection groups, we have the ones that give us the symmetries for the m-gons, and that's for m equals 3, so the symmetries of the triangle, m equals 4, so the symmetries of the square, and so on for the pentagon, and all the way up to polygons with as many sides as we like. So that's what's going on down here. What about these entries at the top here? And so what do we mean when we say an? Well, an is just notation for this Coxeter diagram where we just have n nodes and they're all in a line. Okay, so this is a2, for example, and you might recognize this as describing the symmetries of the triangle. Okay, we already did an in-depth example looking at this. This is telling us about the symmetries of the three-gon. What about a3? Well, a3 here looks like this. And if we remember how Coxeter diagrams correspond with Schläfli symbols, we can see that this Coxeter diagram here corresponds to this Schläfli symbol here, which corresponds to our regular tetrahedron. So this A3 Coxeter group is the same thing as the symmetry group for the tetrahedron. And remember, the tetrahedron has these 4 vertices, so its symmetry group is basically the symmetric group on 4 elements, which is also called S4. And so we can continue looking at A4 and A5 and so on. And so what this top line of our table is really telling us is that in this kind of list of finite reflection groups, we should be including the symmetry group of the n-dimensional simplex. And that symmetry group, that finite reflection group, is called AN. And the sort of corresponding Coxeter diagram is just n nodes in a kind of chain. So that's this row here. What about this next row? Well, this is the symmetry group for the hypercube. Okay, Bn is the Coxeter group for the hypercube, or, equivalently the cross polytope. And so we've already seen an example of this as well. And so remember, we already checked out how to think about the symmetries of the 3-dimensional cube using these kind of Coxeter diagrams. And so this is the Coxeter diagram corresponding to the 3-dimensional hypercube. And remember again that the Schläfli symbol for the cube is 4,3. And you see how this corresponds to this kind of notation here when we remember that these kind of unlabeled nodes should be labeled with a 3. Okay, so there's just one more row left that we need to understand, and that's this dn here. Well, by now we sort of know how to read these Coxeter diagrams and interpret them both geometrically and in terms of symmetries, but we can also ask what kind of shape is this giving us the symmetries of? And it turns out that in general, the answer is not going to be a regular polytope, but it's going to be a demicube, okay? The demicube in n dimensions. So if you get an n-dimensional hypercube and you take every other vertex, as I was describing before, you call that resulting polytope the n-dimensional demicube. And dn is giving you the symmetries of that. At least I think that's the case. I haven't verified that in general numbers of dimensions, but I have heard other people say that that is the case. And a particularly interesting example of this is this case D4 here. Actually, we should probably start at D4 because it's difficult to know what this notation means when you have less than 4 nodes. But this case here, where we consider D4, is a really fascinating case. And we're going to come back to this later when we have some more tools, and we're going to see how this is like really closely related to the 24 cell and all sorts of fascinating geometry. And so there we have it. Coxeter groups can answer fundamental questions about the nature of all of the different symmetries that are possible, even in high-dimensional spaces. And they can also allow us to construct all of these regular polytopes. Now, before I change topic a little bit, let me just show you one other fascinating thing that you can get out of these Coxeter groups. So I'd like you to think about the following situation. Let's suppose that I give you a load of squares, and I tell you I want you to stick these squares together in some kind of a regular way. So if you stick them together so that 3 squares meet every vertex, then you're going to make a cube, and that's going to have Schläfli symbol 4,3. So the Coxeter diagram is going to look like this. We've already seen this. However, you could also do something different. You could just keep everything flat, keep everything in the plane, and you could make this kind of tiling of the plane with squares. This tiling goes on forever, and in that case, you're going to have 4 squares meeting every vertex. So this is not corresponding to a regular polyhedron. This is corresponding to a sort of infinite tiling or honeycomb kind of structure. And is it okay to use something like a Schläfli symbol to describe this? Well, yes, it is. Okay, so we can describe this kind of infinite tiling with this Schläfli symbol here, which makes perfect sense, right? We're saying it's made out of polygons and we have 4 of them touching every vertex. But can we go further? Can we actually do the usual jump from Schläfli symbols to Coxeter diagrams? Well, yes, we can. We can write down this Coxeter diagram here. But how are we supposed to interpret this? Well, if you remember, we had this way of approaching this problem by thinking about this kind of spherical simplex that has vertices basically corresponding to our outer special points. And then really, we thought that the Coxeter group is telling us how we should be reflecting the stuff inside our kind of spherical simplex around the sphere to give us this kind of regular polytope structure, this kind of tessellation of our hypersphere. And it turns out that basically we can apply a similar kind of method here, except we won't be dealing with a spherical simplex, we'll be dealing with a flat simplex. So it's actually a lot simpler than I'm making it sound. If we want to interpret something like this, the best way of doing it is to say, I'm going to work in 2-dimensional space instead of 3-dimensional space, and I'm going to think of each of these as a 1-dimensional hyperplane. And again, these numbers here are telling me the angles between these different planes. And so we're going to end up with a region that looks like this, okay? We're going to have 2 angles of pi over 4 corresponding to these 2. And remember, there's this kind of hidden edge like that, showing us that the planes corresponding to the first node and the third node are perpendicular, okay? So this is really the situation that we're having described here. And then if you make these 3 walls here that I've drawn in red, if you make those into mirrors, well, now we have mirrors on every side of our simplex. And then if you reflect in those, you know, it's like if you stand in an elevator and you have a mirror in front of you and behind you, you're going to end up with this kind of infinite array of reflections. And actually, what that's going to look like is this infinite tiling of the plane here. So really, this infinite tiling, a good notation for it is this. So you see how powerful this technique of Coxeter groups is, not only for these finite reflection groups, but also for these situations corresponding to these kind of honeycombs in n-dimensional space, where we have these kind of regular configurations that go on and on forever. Okay, so that's it. We made it. We've understood what Coxeter groups are. We've understood what regular polytopes are. We've understood all finite reflection groups. I think you should be proud of yourself for watching this video so far. If some things haven't been clear, of course, you can always watch things again. I've got tons of resources linked in the description to this video, but now basically we're on the easy street. So what we're going to do for the rest of this video is we're going to look at some other perspectives on the same phenomena. We're basically going to look at how we can understand the same kind of ideas using some different tools. And some of these tools are really, really going to help us. They're going to make things much more concrete and computational. And we're going to be able to answer questions like, how do we deal with all these reflections in high dimensional space? And actually, we're going to get to some even more fascinating and kind of mysterious things that are happening here. Hopefully, you've already felt that there's been some kind of mystery about what we've been doing. I mean, somehow we've sort of described what all of these regular polytopes are, but the answers that we've obtained have seemed kind of strange, right? Like, why is it that we have, for example, the 120 cell and the 600 cell, these enormous 4-dimensional regular polytopes, and then suddenly there isn't an analog of those things in 5 dimensions or high dimensions? Why should reality be set up that way? And what's going on with these exceptional groups, E6, E7, E8? And why is it that these strange one-off beasts are appearing in the answer? So if you take a look again at these diagrams on the left here, well, maybe you can see that there's something a little bit special about these rows, the AN diagrams and the DN diagrams, and also the E6, E7, and E8. Now, the obvious special thing about these diagrams is that they only have unlabeled edges, or if you like, all of the kind of edges in these diagrams should be labeled with 3s. There are no 4s or 5s or other numbers appearing in these Coxeter diagrams. So geometrically, this is telling us that these are situations where the angle between any two hyperplanes is either going to be pi over 3 or pi over 2. And so you could say that these are special cases of our Coxeter groups for that kind of reason, but that seems a little bit arbitrary. But it turns out that actually the AN, DN, and sort of E6, E7, E8 are very, very, very special, because not only are these things Coxeter diagrams, not only do they appear from these kind of fundamental questions that we've been tackling so far, they also appear in mathematics in so many other areas. So there's something really, really strange going on here. If you look at Lie theory, which we're not really going to discuss directly today, or if you look at this kind of Dynkin theory involving lattices, which we are going to get into, you see exactly the same diagrams appear. And the same diagrams also appear in all sorts of other places in mathematics that you wouldn't even expect to be related to Coxeter groups. So there's something very, very peculiar going on here. And when you couple this with the fact that things like E8 might be describing like the fundamental laws of physics, it really gets extremely interesting. So what we're going to look at now is we're going to look at the AN, DN, and sort of EN diagrams, but we're going to look at them from a different sort of perspective. You see, I've been talking a lot about reflections, and I've been telling you that there are easy kind of computational or linear algebra based ways to think about these kind of things. Well, actually, I'm just going to focus on these kind of AN, DN, and EN kind of diagrams from now on. I'm going to call those ADE graphs. That's what they're often called. And so basically, when we focus on those, we're going to find that there's an absolutely beautiful theory which allows us to think about these things in a really computational way. And basically, all these mirrored hyperplanes are going to be related to vectors, and they're going to be forming these beautiful kind of lattice structures. So I really want you to understand here that the hard work has been done. Everything that we do from now on is just consolidating the knowledge that we've already got. Okay, this is going to make things easier. So I'm going to start with this kind of example involving our A2 Coxeter diagram, because we've already seen this. Okay, so there's a lot going on in this picture, but for now, the only thing I want you to notice is that if we concentrate on this orange triangle here, and we look at the long red line and the long blue line, those should remind you of the situation that we've already encountered. If we think of this big orange triangle here as our equilateral triangle, our polytope that we're trying to understand the symmetries of, remember our kind of starting step was to draw this long red line, which would be a mirror, and then this long blue line, which would be a mirror. And so you can see that that kind of structure, which we already have, basically can follow us down the same line of reasoning involving kaleidoscope and fundamental regions and things. That's the story that we've already understood. And now what we're going to do is to see that there's another way of thinking about this story, and it's really simple. Basically, I just want you to notice that we can draw things so that we have this thick red arrow, which is perpendicular to our red mirror, and we have this thick blue arrow, which is perpendicular to our blue mirror. And these two vectors, these two arrows which we've just drawn, are going to be very, very useful for us to understand more about what's going on here. So we're going to see very shortly that there's some really nice linear algebra which basically lets us talk about reflections in terms of these vectors, okay? Because we've been talking a lot about the idea that if you have n-dimensional space and you have a n-1 dimensional hyperplane, then you can reflect stuff in that hyperplane. But how do you describe an n-1 dimensional hyperplane? Well, one way you can do it is by giving a vector which is perpendicular to that hyperplane. And it turns out that if you think about things in those kind kind of terms, there's some really easy to understand kind of linear algebra that can let you see what those kind of reflections are going to do to space. Really, you can think of this thick red arrow and this thick blue arrow as kind of giving us the information about these mirrors, the long red line and the long blue line, respectively, because those mirrors are perpendicular to these thick vectors. But you can see that actually there's something more going on here, because you can see that if we think about adding together sort of combinations of this thick blue arrow and this thick red arrow, we can kind of put these things head to tail, and we can think about integer combinations of these vectors, and actually that's going to give us this lovely kind of triangular lattice shape. So you can see that we have this triangular lattice shape, which is this sort of triangular tiling of our entire space. And this is actually called the A2 lattice. We're going to understand this from first principles in a totally geometric way. So things are about to get really, really simple again. But what I'm just trying to illustrate here is that this story of these so-called ADE lattices, these are basically these lattices, these kind of infinitely repeating patterns, which have the same kind of symmetries as these finite reflection groups corresponding to these ADE graphs. Basically, we're going to see these lattice structures appear. And this is really complementing our understanding of these finite reflection groups and these kind of Coxeter diagrams. Okay, so actually when I made this video, I kind of made it in two parts. And so we're actually approaching a part of this video where everything is going to get super simple and completely geometric. And I'm going to throw in all sorts of 3D models, and there's going to be interviews with people where we're talking about geometric concepts. We're about to sort of go into a kind of geometric heaven where everything gets really, really easy. And so just before we return to this kind of intuitive land of picture-based reasoning, I just want to lay out the final bits of terminology that are going to be useful for us as we discuss all this stuff. Now, some of the notions I'm about to define do rely on some terms from linear algebra. And if you don't understand them, don't worry. I really believe that you're going to be able to follow the video regardless. But I want to get these final definitions done with. So let's go. So now we're moving into a discussion of lattices. So what is a lattice? Well, roughly speaking, it's some kind of repeating configuration of points in space. But we can actually be a bit more precise than that. So let's say we have n-dimensional space and we have a basis for that space. So these n vectors here are forming a basis. So this is an example in 2 dimensions. Well, then the corresponding lattice just corresponds to all of the integer combinations of these basis vectors. So basically, we want to be thinking about all the vectors that we can write in this kind of form here, where k1 and k2 and so on are all integers. For example, we can refer to this point here in our lattice as 2 times v1 plus v2, because we can get to this vector from our starting point here by doing v1 twice and then going along v2. So that's what a lattice is. This next thing we're going to encounter is really fundamental. So I want to tell you about it now, but we're going to revisit this several times. And at some point, I'm actually going to go back to basics and really give you a very in-depth motivation for why this kind of thing is working as it is. So don't worry if this seems complicated at this point, but let me show you anyway. So what are we doing here? Well, basically we're talking about this operation where we're going to be reflecting things in a hyperplane. This is how we describe reflections in hyperplanes using linear algebra. Let me just read through this, although like I say, don't worry if you don't understand, because we're going to come back to this again later. Suppose we're in n-dimensional space and we have a vector v. And then what we want to do is we want to reflect everything in this hyperplane here, which is perpendicular to v. Now, a good notation for this hyperplane is v-perp. And so you can say that what we're really doing here is describing this operation here where we're reflecting everything in the hyperplane that's perpendicular to v. And so how does this operation work? What happens if we have a vector w and then we want to reflect it in the hyperplane perpendicular to v? Well, the result here, by definition, is going to be s v-perp of w. So s v-perp is this operation that we can do on w, and it gives us this result of reflecting w in this hyperplane. And what I want to get across here is that there's a very, very simple formula which actually tells us what this resulting vector is going to be. And the main thing that I want to get across here is that this is actually really easy to think about geometrically geometrically. We don't have to think about anything high dimensional here. Why not? Well, basically, because even if we're working in a billion dimensional space, it doesn't matter. This situation is essentially just kind of two-dimensional. So why do I say that? Well, basically, we have this vector v, and then we have this vector w. And what we want to do is reflect w in the hyperplane perpendicular to v. But you should notice that when we have these two vectors, v and w, and we just look at those, there's going to be a two-dimensional subspace that contains those two vectors. And we can just focus on what's going on in that two-dimensional subspace, because the result of this reflection is also going to be in that subspace. So basically, we can sort of section off the situation we're looking at and just look at the kind of two-dimensional situation. And actually, we have this formula here, which tells us exactly what the result is of reflecting w in the hyperplane perpendicular to v. And this here is the dot product. We're going to get into all this much later. And so while I'm going through all these definitions, let me do the big one now, which is this definition of a root system. So this is probably unnecessarily abstract, because I really believe you're going to understand everything that's going on through direct examples. I'm really just trying to build up some kind of terminology here that we can use to describe all these things. But honestly, you're not even going to need to know this to get into the examples. So don't stress about assimilating this definition, but I would like to tell you what it is. So if we have n-dimensional space, r to the power of n, and we have a subset of that space, phi, then we say that phi is a root system when it satisfies a few conditions here that I'm going to discuss. So phi should be a finite set of non-zero vectors which meet these kind of conditions here. So what are these conditions? Well, the first one says that phi spans our n-dimensional space. So you can get any point in n-dimensional space by taking some linear combination of vectors from phi. And our second point here says that if we take a member w of this set phi, well, we can ask what kinds of multiples of w are going to themselves be members of phi. What can we times w by so that the result is also in phi? So the next condition we need phi to satisfy is this one here. What this one's saying is that if we pick a member w of this set of vectors phi, then the only kind of multiples of w which should lie in phi are w itself and minus w, which is like minus 1 times w. So 2w won't be a member of phi. 0.7w won't be a member of phi. These are the only multiples of w which will also be members of phi. Our next condition is this one here. So what's this saying? So roughly speaking, what this is saying is that this kind of set of vectors should have the same kind of symmetries as the kind of finite reflection groups that we've encountered before. To be more precise, what exactly we're requiring with this condition is that if we pick any two members of our root system, v and w, then we require that if we take w and reflect it in the hyperplane perpendicular to v, we get another member of our root system. And then this is the final condition here. Basically, this final condition is saying that if we take any v and w from phi, then we have to have that this quantity here has to be an integer. What does this mean? Well, basically, if we take a look at our formula here, which is telling us the result we get when we reflect w in the hyperplane perpendicular to v, we can see that this is the result here. And we're insisting that this number here should be an integer. So basically what we're saying here is that we have a lattice, and this lattice has all of these symmetries. It has this feature that when we reflect things in one of these specially chosen hyperplanes, like our red line here, then that's going to send points on our lattice to points on our lattice. But moreover, when we're in the root system, the result of this reflection can itself be described just by adding on a certain kind of integer combination of these root vectors. That's a very kind of hand-wavy explanation of what's going on. Of course, if you want to be formal, you can see what I'm saying exactly here. And a root system is precisely defined by this definition, a finite set of non-zero vectors that satisfies these four conditions here. So that's the the final hurdle. We're going to gain a lot more understanding of what these root systems really are as we look at some practical examples. So let me just finish this terminology rundown and then we can get back to the geometry. So we have this idea of a root system. It's a set of vectors, and those vectors are sometimes called roots. Now, associated with all this stuff, we have something called the root lattice. The root lattice generated by the root system just consists of all of the integer combinations of the vectors from that root system. So in this case, we're seeing the A2 lattice, and the root system just consists of these 6 vectors here, these 6 arrows that are emanating from the middle here, that are sort of pointing out these different points of the hexagon. So we have 2 blue arrows, 2 red arrows, and 2 green arrows. We're going to see how this comes about directly very, very shortly. So that's our A2 root system, and then our A2 lattice, well, that's just this whole grid with all these points on, okay? So all of these black dots, all of these kind of vertices in this triangular tiling of the plane here, our A2 lattice constitutes all of those points because they're all of the kind of integer combinations of vectors from this root system that we are going to get. Okay, so that's it. We're ready to look at everything in this intuitive geometric way. And so let's just have a little preview of what kind of things are going to be coming up. So we want to be looking now at these kind of lattices that are associated with our ADE graphs. So we're going to be looking at different diagrams, for example, these AN diagrams here. We've already had a look at something associated with this A2 diagram here. And so more generally, when we have the AN diagrams, so we can think of that as the Coxeter diagram where we have n nodes connected in a chain, well, we have this associated so-called AN lattice. So what is the AN lattice? Well, it's a sort of lattice in n-dimensional space, which has an extremely beautiful structure. This structure is extremely pleasing and beautiful, and it also has a very simple definition mathematically. The AN lattice is basically this kind of n-dimensional lattice, and it can be described like I'm writing here. What we can say is it consists of all of the points in n+1 dimensional space, which have integer coordinates that sum to 0. At first glance, you might be a bit confused here because I said that this is a lattice in n-dimensional space, but I'm actually talking about these points here that live in n+1 dimensional space. Basically, the reason why this makes sense is because even though we're talking about these points here as if they're in n+1 dimensional space, actually they turn out to be lying on a particular hyperplane. So even though we're describing our points of the AN lattice like this, it turns out that really they're forming just an n-dimensional hyperplane. This is going to be easy for us to understand once we've had a look at more examples. What we're saying here is that we have this kind of AN lattice, which is this root lattice with symmetries as described by this AN Coxeter group, this finite symmetry group. And so this kind of lattice-based perspective gives us a fresh kind of approach to think about what we can get from these kind of AN diagrams. So it turns out that there's also a DN lattice when n is greater than or equal to 4. So there's going to be a root lattice associated with this D4 diagram here, and another one associated with this D5 diagram here. In general, what's the DN lattice? Well, it just consists of all of the points in n-dimensional space which have integer coordinates that add up to an even number. And so once again, once we see examples of this, you're going to see how intuitive and beautiful this kind of idea is. And then finally, we're also going to see that there are lattices associated with E6, E7, and E8. And so the absolute final technicality, final definition that I want to get across, and then we're totally in picture country, is this one, the idea of a basis of a root system. I don't think it's at all necessary for you to know this definition thoroughly, but I want to give you the definition for completeness. Let's say we have a root system phi, and then we say that a subset B of phi is going to be a basis for our root system phi when these two conditions here are met. This first condition says that B is a basis for the vector space which is spanned by phi. And then this second condition just says that when we take take any member of our root system, W, well, we can write that W as this kind of integer-weighted combination of these members B1, B2, and so on up to Bm from our basis. So we can find these members B1 all the way up to Bm from this set capital B, and we can weight each of those by an integer, and then we can add up the results, and this integer linear combination here is going to give us W. But moreover, this works in such a way that either all of these k's here, all of these kind of weights, are either all non-negative integers or all non-positive integers. So admittedly, this is a bit of a difficult definition to pass on a first take, but don't worry, you don't need to know it at all. Now let's get back to the beautiful, geometric, intuitive, picture-based way of thinking about all of this stuff. So I'm going to start by explaining these ideas in a purely geometric way by talking about things like this crystal lattice here and the hypercube and the good old 24 cell. So we're going to have a good look at these regular polytopes. These are some of the most beautiful structures in mathematics, and you're going to see why. But we're also going to look at a sort of general theory of this stuff, and we're going to look at it through several different angles because it's very strange. Basically, there are these special objects which relate to this sort of theory of lattices and regular polytopes and all sorts of other things in maths. But it's very peculiar because, number one, there are just a few extraordinary objects, one of which is E8, which has been proposed to be giving a fundamental theory of physics. So not only are there these extraordinary structures, but they sort of manifest themselves in varying extraordinary ways in different parts of mathematics. We're seeing the same kind of structure from totally different places in ways that you wouldn't expect. So I sort of liken this to the sun. It's a sort of singular thing which you can see from lots of different perspectives, and it's essential for mathematics. So I'd say there's, in a way, sort of two different ways that mathematical objects can be important. A bit like in nature, we can have things that are really multifarious, like bacteria. They're obviously very important for the Earth because there's so many of them. They make a lot of things happen. But we also have these sorts of one-off structures like the sun and the moon and the Earth itself, which are really essential for everything that happens as well. But they have a sort of different nature. They're sort of important because they're singular and they're sort of so big and structured. And it's similar in mathematics. So if you look at, for example, these Platonic solids, I've got a 12-sided dice here, which is a dodecahedron shape. And here's an octahedron. So if you look at these, again, they're extraordinary in sort of how rare they are. I'll talk more about Platonic solids later, but they're again extraordinary, and part of the reason is because they are unique, and that makes them sort of emblematic of some really important symmetries that we find in reality. Okay, so what I want to show you is a family of structures, and I want to start with one of the simplest and most fundamental, and it's the triangular lattice. It's basically where you have a load of equilateral triangles on a plane which tile the whole plane. I'm sure you've seen this pattern many times before, but I want to show you a very lovely way we can generate this pattern geometrically. What I'm starting with here are these two arrows or vectors, which are 120 degrees apart, or a third of a turn apart. And so now we're going to do some constructions. So I'm going to make a line that's perpendicular to this blue one. And I'm also going to make a line that's perpendicular to this red vector. And now what we're going to do is we're going to think of these new solid lines that we've just drawn as mirrors. And they can reflect things. And by looking at what gets reflected in these mirrors, we're going to see this kind of triangular lattice or this sort of hexagonal shape appear. So what happens if we reflect this red vector here in this blue mirror? Well, we get this green vector here. So, okay, what else can we do? Well, we have this red line and we have this blue mirror. So what happens if we reflect the red line in the blue mirror? Well, we get this green line. And you should also notice that this green line is perpendicular to our green vector. And so we can think of this green line as a mirror as well. I mean, it's a reflection of a mirror. Why shouldn't it also be a mirror? And then we can reflect the blue arrow in the green mirror. And we can reflect the red arrow in the green mirror. And we can reflect this new dotted blue arrow in the red mirror. And so now we've got it. We've got our 6 arrows, which are going out in these 6 equally separated directions. And so this structure here is what's called the root system of the A2 lattice. So as such, this has various special properties. For example, if we take one of these vectors here, one of these 6 members of this root system, and we take the sort of hyperplane that's perpendicular to it, well, that's just the line that's perpendicular to it. Well, if we reflect vectors in this root system in such a line, we get other vectors in the root system. So as you've already seen, when we sort of do these reflections in the red, green, or blue line with one of these vectors, we get another one of these vectors. And so the really fascinating thing is what we can then do is take integer combinations of these root vectors, and this fills out our triangular lattice. So we could include another green dotted vector here, for example. And so now we're pointing over here to this sort of dotted green vector plus dotted green vector point. And so we can carry on adding in all these different combinations of these vectors. And you can see that this is going to fill out this triangular lattice. And we have our root system in the middle of this. And what I also find really extraordinary here is that we started by thinking about mirrors. And actually, we can make this whole pattern by properly placing mirrors. We'll see that later. And so this kind of triangular pattern that we have is called a lattice. So what's a lattice? Well, lattice in n-dimensional space is when we have a basis for the n-dimensional space. So, that's a load of vectors that we can use to express any point in our space. And we can do that in a unique way. Well, when we have a setup like that, where we just take the integer combinations of those vectors, the resulting structure is called a lattice. So why is this a lattice? Well, you can see that if we take our original vectors, the blue one and the red one, say, then we can express any point in this triangular lattice as some kind of an integer combination of this red and blue vector. For example, this point here at the top, we can get to that by going along one blue vector and then -1 red vector. So we could call this point blue take away red. Or if red is our first vector and blue is our second, then we could give this point coordinates 1, -1. And then these roots are these sort of generators of this lattice. They have the feature that if we take one of these vectors and then we take the line or the hyperplane more generally perpendicular to it, we reflect in that hyperplane, we get other roots. So that was the A2 lattice, which is basically 2-dimensional. The next one I want to get to is the A3 lattice. Now, this is a thing of physical and mathematical beauty. It really is. It corresponds to the tightest way that you can pack spheres into 3D space. So if you want to pack oranges, for example, as densely as possible, then you're going to end up putting them in this sort of pattern. By this, I mean that if we idealize our oranges to be spheres, and then we imagine there's a point in the center of each of those spheres, then those points are going to form this A3 lattice shape, which is a lattice in 3 dimensions. And this A3 lattice is also extremely important in chemistry because it corresponds to the configuration of atoms in many materials, for example, gold. Now, this A3 lattice is also sometimes called the face-centered cubic lattice. And that's because there's a very, very straightforward way to think about it. What you can do is get a load of cubes and then slot them together in the obvious way to fill space, and then mark out the centers of the faces of all of those cubes. And so those marks, together with marks on the vertices of the cube, are going to form this face-centered cubic lattice. And yet another way we can think about this beautiful structure is it can be built out of these regular octahedrons, things like this shape here, together with tetrahedra. And you can see how this works indicated by this picture here. And that's why this lattice has another name. It's sometimes called the tetrahedral octahedral honeycomb because it's made out of these octahedra and tetrahedra, and honeycomb because it has this sort of repeating pattern, this sort of lattice structure. And so there's an absolutely beautiful way to look at this A3 lattice among several other fascinating lattices, which is by using a sort of construction like this. The most highly regular kind of 3D lattice is the cubic lattice, as in just stacking a load of cubes together. If you put points in 3D with these sort of X, Y, Z coordinates as integers, then you can basically see the form of this most basic cubic lattice, and it just corresponds with all of these different points here, and obviously a lot more because it goes on forever. The thing that you can do next is very interesting. you see that I have a coordinate system here. So you can see that this is at coordinate 1, for example. This vertex here has coordinates 1, 0, 0, because the number of steps that way is 1, and the number of steps in the y direction and the z direction are both 0. So this has coordinates 1, 0, 0. And you can see that all of these points of this kind of cubic lattice are these points where x, y, and z are whole numbers. So then what I'm doing is I'm coloring the points of the plane according to a certain scheme. The easiest way to demonstrate it is like this. We see that we have all these points which are sort of formed by filling space with these little cubes of length 1. But what if we start to throw down cubes of length 2 instead and fill space with those? So here I've just thrown down a cube of length 2, and you can see that what we're doing is we're coloring points black when they correspond to the vertices of such cubes. The edge midpoints we're coloring red, the face centers we're coloring green, and the kind of body centers of the cube, the things that are right in the middle of these big red cubes, we're going to color those blue. And you can imagine this pattern being continued, right? So we can put another big red cube next to this one, and we can keep coloring. I mean, it takes a long time to do in GeoGebra, but one can imagine this pattern going on and on forever. Another way you can think of it, I'll just say quickly, is that you can imagine that these colors, black, red, green, and blue, are corresponding to how many of the 3 coordinates of a given point are odd. No odd coordinates, that means black. 1 odd coordinate, that means red. 2 odd coordinates, that means green. 3 odd coordinates, that means blue. Don't worry if you don't get that. We're not going to come back to that idea. But I mean, the real point I wanted to get across is that we can make a lot of these lovely structures in 3D now by connecting together points of different colors. And so when we just consider the green points and the black points, well, the black points correspond to the vertices of these big cubes, and the green ones correspond to the centers of the faces. So yes, we have a face-centered cubic lattice. But by joining these together, we can see that we have this octahedron shape here, and you can also see these tetrahedra as well. And so while we're here and looking at this geometry of lattices, I can't resist just mentioning another thing. When we have all these different colored points in 3D, we can think about connecting together various combinations of them. So this is considered in chapter 4 of Coxeter's book, Regular Polytopes, and it's very fascinating. And I think, I haven't double checked this, but I think if we connect the green and the red points, we get this other beautiful pattern that I'll show you now. So this is another one of these sort of close to regular kind of honeycomb structures. And this one, I'm just showing a bit of it here, but it's formed by having these cuboctahedra and also octahedra. So I'm only showing part of it, but hopefully you can imagine how to fill this out. You start off by filling space with these red cubes, and then inside every red cube, you slice the corners of that cube away by sort of slicing through the edge midpoints of that cube. You used to have a cube there, like at the top right here, and now you have this cuboctahedron because you've cut away the corners. And so you have this cuboctahedron, that's all that's left. And so now if you do this to every red cube, then you end up with these cavities where you remove some of the material, and those cavities form these octahedra here. So we really want to understand this A3 lattice from a mathematical point of view. And so it's going to be very useful to understand about this cuboctahedron shape here. And you can see by this lovely picture that really we can think of this cuboctahedron as what we get when we take a cube, and then we pick out all of the sort of edge midpoints, and then we slice off each of the corners of the cube by sort of cutting a knife that goes through these edge midpoints. And that forms this cuboctahedron. So this cuboctahedron is a really, really important shape. I think it's right sort of between the octahedron and the cube, and it's very, very close to the Platonic solids. And the thing is that we can actually use the cuboctahedron to sort of generate this A3 lattice, and it's pretty much analogous to the case that we just saw with the A2 lattice. Okay, so we're very interested in this A3 lattice. There's so many people who are interested in the flower of life pattern and the sort of triangular lattice and the hexagonal lattice. And I really think that this A3 lattice is sort of equally, if not even more fascinating. I think perhaps it's not so widely appreciated because not many people know about the wonderful features of it. Quite a few people talk about this face-centered cubic in the context of chemistry. I remember when I was doing my physics degree having to remember things about the face-centered cubic, but I feel like there wasn't much emphasis on the sort of geometric features of this thing, which really are extraordinary. So basically, we have a sort of sequence of lattices. First, we have our A2 lattice in 2 dimensions, then we have our A3 lattice in 3 dimensions. Actually, the pattern goes on. We have A4, A5 in 4 and 5 dimensions, and so on. And there's so much to say about these things mathematically. They really are very, very fundamental in mathematics. They are closely related to these symmetric groups, right in the center of group theory. But I'm trying to do a sort of geometric overview. So let's now think back to what we were saying about the A2 lattice. So if you remember, the way I sort of introduced it was to say, well, we start off with these 2 vectors here, sort of separated by 120 degrees. And then I started to generate things, right? So I said, okay, then we can put some mirrors perpendicular to these vectors, and we can start reflecting things. And finally, we ended up with 6 vectors, and then we saw that those sort of filled out to make this triangular lattice. So it turns out that something totally analogous happens for this A3 lattice. But to appreciate this, just think back to the A2 lattice. And actually, you'll remember that those 6 root vectors of A2 pointed out the 6 vertices of a regular hexagon. So really, we started with a hexagon in 2D. And so what we're now going to do is do something analogous to that in 3D. So rather than starting with a hexagon, we're going to start with this beautiful Cuboctahedron here. And you can see what's going on here. My central point here is now this black point. And then to generate this root system, to generate all these vectors, which are going to allow us to build this A3 lattice, what we're going to do is consider the vectors that come out of this black vertex here and go to the red, blue, and green vertices. And that's going to give us these 3 vectors. And then we're going to build up from there, really totally analogously to how we built up from here in 2D. Let's have a look at that. So if you'll forgive me, I'm not going to spend too long on this, but here's the basic idea. We have our Cuboctahedron, and then we have this point in the center, and then we pick out these 3 vectors here. Now we're going to see how we can get these vectors algebraically later, because I really want to tell you how to do this in every dimension. But what we're going to do from here is pretty much proceed analogously to before. So, for example, we look at our red vector, and then we place this plane here that's perpendicular to the red vector, and we think of this as our mirror. And then we keep reflecting things, right? So then we can reflect the blue vector in this plane, and we get another vector. We can also make a plane that's perpendicular to our blue vector, which will be a blue plane, which will be a blue mirror, and then we can reflect in that, and we can use the green one, and so on. And when we do this, what we're going to find is that these 3 vectors that we started with end up kind of getting reflected round until we end up with 12 vectors, 1 for each vertex of our Cuboctahedron. And so it's really totally analogous to the story in 2D. We're just sort of working 1 dimension higher. And so once we've filled out all these vectors, then just like in the 2D case, we can then carry on. So we will have our root system once we're pointing everything out in the original Cuboctahedron, and then we can just carry on taking more and more combinations of the vectors we have. And we're going to fill all of 3D space and point out all of the things inside this face-centered cubic pattern. And I highly encourage anyone, maybe get some zone tools and make a version of this for yourself. I mean, it's endlessly fascinating. When you start looking at this, you'll see so many patterns in geometry, which, if you look at it from different angles, you see all sorts of things. It's really an extraordinary thing. Okay, so there's many different views on the ADE phenomena, and so far I've mostly been focusing on this sort of lattice-based perspective. But let's have a look at another view. So when we speak of, for example, AN or DN, people talk about things like the AN lattice or the DN lattice or the AN root system or the DN root system. So that's very much sort of centered around thinking about lattices. But we can also think about Coxeter groups, and these are related to geometry in a bit of a different way. So let me just do a Google search here. So if I type in on Google NLab Coxeter groups, so NLab is a great maths website where you can get information on all sorts of things. And the family AN is the isometry group of the regular n simplex, identified with the symmetric group Sn plus 1. So NLab is great, but it's kind of cryptic. So let's try and decrypt this a little bit. Firstly, it's saying that this AN group, saying it's an isometry group, meaning it's some group of rigid motions. It's associated with the n simplex, regular n simplex. So this is like a sort of generalization of the tetrahedron. And then Sn plus 1, that's the group of permutations of a set of n plus 1 elements. So here an n simplex is like a sort of generalization of the tetrahedron into n-dimensional space. So the tetrahedron would be a 3 simplex. And what they're saying is that AN is basically the symmetry group of such a simplex. And they're also saying that it corresponds here to Sn plus 1, which is the group of permutations of n plus 1 elements. So there's a lot of information here. And how are we going to connect it with the way we have of thinking about AN already? Well, if you have a look at Wildberger's resources on the mutation game, he has a way of looking at the Weyl group of AN, and there you can see this connection with the symmetric group. And you might know that this symmetric group on n plus 1 elements is the symmetry group of the n simplex. Because, you know, if n is 2, well, if you have a equilateral triangle, the symmetries of that, including if you can flip the triangle over, are basically just corresponding to the different permutations that you have of a 3-element set. So the 2 simplex, as in the triangle, has a symmetry group which corresponds to the symmetric group on 3 elements. But this webpage here is about Coxeter groups. And if we really want to be faithful to the way that Coxeter thought about these kind of things, we want to be thinking about them a bit more geometrically. So we really want to have a sort of hands-on way to study the symmetries of these simplexes. Now, I've been focusing quite a lot on A3, so I want to take a sort of geometric perspective on the Coxeter group associated with A3. And basically, I want to show you how you can think about that using mirrors. And then I want to connect it with the A3 lattice that we've already encountered. So what we want to do is to study the symmetries of the regular tetrahedron. So I fired up GeoGebra, and I've got a regular tetrahedron here. Let's begin with a sort of simple question, which is, what are the lines of symmetry of a tetrahedron? Now, even here, you might be wondering what I mean by this. How can a tetrahedron have lines of symmetry? It's a 3D object, right? This is already quite interesting. Think about a triangular tiling of the plane. If I tile the plane with equilateral triangles, then you would be happy for me to speak about things like the lines of symmetry of a pattern like that. And there would be many. But now, if we look at a tetrahedron, you can also think of it as something like a sort of tiling, but it's a tiling on a sphere. We now have these triangles, but these triangles are not all laid flat. They're laid around in a sphere. And so we can sort of speak of lines of symmetry again. Actually, better to really think of them as great circles. If I draw a sphere like this, well then, because the sphere is sort of see-through, you can imagine that these points that I'm drawing here, you could imagine sort of moving them outwards a bit until they lie on the surface of the sphere. And then you can see that, well, we might not want to call them lines of symmetry, but they're really more like great circles, or we could almost call them planes of symmetry. So if I draw a plane here, well, 3 points define a plane. So let's define a plane that goes through this vertex here, this edge midpoint, and the center of gravity of the tetrahedron. So you can see I've drawn this plane here, but really the way that the plane is interfacing with the sphere, it's really just giving us a sort of great circle. of the sphere. A great circle of a sphere is a circle that goes around the sphere and has the same center as the sphere has. And so you can see that from a sort of spherical geometry point of view, this is sort of like a line, right? If we're to think of the tetrahedron as something like a tiling, but in a spherical way, then this sort of great circle is sort of like a line of symmetry. And so I'm interested here in what sort of points this great circle's passing through. You can see that on the sort of underlying tetrahedron, I've marked out the vertices and the edge midpoints. And so I actually want to extend these out so that they actually go all the way to the outside of the sphere. Because then what we can do is we can sort of follow around this great circle and we can see what sort of points we encounter. So at the top here, we encounter a vertex, then we encounter an edge midpoint, and then a vertex, and then keeping following it round. Next, we encounter a face center, and then an edge midpoint, and then a face center, and then we're back to the original vertex again. So that's the nature of one of these sorts of lines of symmetry of the tetrahedron. And there's going to be 6 of those, one for every edge of the tetrahedron. You can see that this one's sort of defined in a sense by picking this edge here. So, okay, now we get to the really interesting bit. You see I've selected these 3 points here on the sphere. So one of them, the red one, is a vertex of the tetrahedron. The blue one corresponds to a sort of edge midpoint. I mean, I've pushed it out to the surface of the sphere, but it's lining up with this edge midpoint of the tetrahedron. And the green point corresponds to a face center of the tetrahedron. But again, I pushed it out to be on the surface of the tetrahedron. So what we're going to do now is draw some planes. We'll draw a plane going through this red and green point in the center of the tetrahedron, and a point going through this green and red point in the center. And so now you can see that there's what we could call a spherical triangle. So it's made from these great circles that go through these 3 special points. The angles on this triangle are pretty interesting. The angle at the blue vertex is 90 degrees, and the angles at the other 2 vertices are 60 degrees. So that is interesting. It exceeds 180 degrees, but that's what happens when we have these triangles on spheres. But then what's very, very interesting is that now what we can start to do is we can actually start to reflect these points around our sphere. And basically these 3 planes that we've just drawn, we can think of those as mirrors. And it's basically a similar sort of thing to what we were thinking about before. If we just use these mirrors and reflect everything, we're going to get a lovely pattern which permeates across the whole sphere. So let me show you how this works. So if we take this point, this red point here, and reflect it at this plane, well, we get this vertex down here of our tetrahedron. Now let's get this and reflect it in this plane. Well, we get the other vertex. And then if we get this and we reflect it in this plane, we get the 4th vertex. So you can see that we get all of our 4 vertices by reflecting, starting with this red vertex. What about if we start with the green vertex? Well, if we start with the green vertex and then we reflect it in here, we get this vertex over here. Then if we reflect this in this plane here, we get this point, and reflect this down here, we get this point. And if you look at it, you should notice that these 4 green points are actually forming another tetrahedron, a tetrahedron which is facing the other way around. And so what we're actually getting here is this kind of shape here, which is sometimes called the stellar octangular. It's basically 2 tetrahedra, one's pointing up and one's pointing down, and they pass through each other. When you see this shape, there's 2 very interesting questions you can ask yourself. One is, what is the intersection of these 2 tetrahedra? And if you think about it for a while, you'll realize that the intersection of these 2 is a regular octahedron. So that's very interesting. Another thing you can ask is, what is the sort of convex hull? In other words, what's the sort of smallest polyhedron which could contain this shape? And the answer is a cube. Okay, so another way you can get this same shape, you take a cube and then you pick every other vertex Well, that forms a tetrahedron. And then you'll get another tetrahedron using the vertices that you didn't choose. And those are two interpenetrating tetrahedra forming this stellar octangular. So perhaps I can convince you of some of this. What I'm going to start doing is linking red vertices to nearby green vertices. And as we do this, we're going to see that we get a cube. So here's our cube. But we're not done yet, because this cube is what we got just by reflecting around our green vertex and our red vertex. You see, what we're doing here is we're starting off with this spherical triangle in the middle here, this, and then we're sort of reflecting everything around using the planes that we have. But we haven't done any reflecting of this blue vertex here. So let's start reflecting that. And so maybe before I begin, you might want to have a guess at what kind of shape the configuration of the images of the blue vertices is going to form. So, okay, we take this blue vertex and we reflect it in this plane here. And then we'll carry on, reflect. And then the final one, so we've just got to reflect this point here in this plane here, and we're done. So now we have these 6 points, which are nicely spaced out on the sphere. And can you think of a nice regular polyhedron that has 6 vertices? Well, it's our friend, the octahedron again. So these 6 points here are forming an octahedron. So we have a cube, and we have this octahedron formed by these blue points here, and they're going to have a special relationship with each other. So this octahedron, it's these 2 square-based pyramids. One's pointing downwards like that, and then we just have to connect these 4 up to form the other. And so you see how much lovely geometry we're getting just from starting with this spherical triangle and reflecting it around. We have now a cube, which we can really think of as formed by 2 sorts of tetrahedra. And then we also have this octahedron, and also the octahedron is sort of in the dual configuration to the cube, in that the octahedron kind of has vertices in the center of the faces of the cube and so on. So you can see that this sort of Coxeter view of A3 is very, very rich. But how is it related to the A3 stuff that we've already seen? We saw an A3 lattice. We saw a cuboctahedron. Where's the cuboctahedron here? So I think there's a couple of ways to answer that. One of them is to say, well, what we have here is 14 points. We've got the 8 vertices of the cube and the 6 vertices of the octahedron. And those 14 points correspond to the vertices of a shape called the rhombic dodecahedron. Here's one of those. And the dual of that is the cuboctahedron. So that's one way we can get to our cuboctahedron, but it's not particularly enlightening to look at it like that. There's a much nicer way to look at it. Really, what we can ask ourselves is, well, what did we do and how does it relate to the kinds of geometry that we did earlier? And really, I think you'll agree that the main thing that we've been doing is reflecting stuff, right? We started with these 3 points on a spherical triangle, and then we just did loads and loads of reflecting. And we were reflecting in these 3 special planes that I've drawn. But in the earlier geometry, what we had were these vectors, these root vectors. And we took these root vectors, and then we looked at the plane that was perpendicular to them, and we reflected in that. And so the lattice view is a sort of vector first view, whereas this view is a sort of plane first view, where we sort of start with the mirrors. But we can go to the other configuration. And so what about if we take these 3 planes here and we draw vectors that are perpendicular to them? Actually, it's easier in this geometry package. I can just draw lines that are perpendicular to these 3 planes. And then we're going to see the connection with the sort of lattice view of A3. If we draw a line that goes through the center of the sphere and is perpendicular to this plane, well, there it is. Oh, well, this line that we just drew, it just happens to pass through the common edge midpoint of our octahedron and our cube. Is this a coincidence? No, it is not. So let's do the same thing for another plane. So we pick the center of our sphere and another plane, and we get another line that happens to go through one of these edge midpoints common to the cube and the octahedron. And so just to finish the job, again, we're going to draw a line through the center of our sphere, but now that's perpendicular to this third plane. And then we've got our third point. So now, I know this drawing is getting a bit messy, but we've drawn three vectors. If we direct these lines in the proper way, we've got three vectors. And these three vectors that we have actually form the basis of the root system of the A3 lattice. So these are really three vectors that are pointing out three different vertices of the cuboctahedron. So I realize that this is getting a bit complex. So let's try and clarify a few things. So firstly, what I have here, if you look at the black line segments carefully, you can see that there's really a cube and a octahedron that are sort of overlaid with each other. And here's a sort of neater picture of that. And if you look carefully at this, you can see that the sort of intersection of the cube and the octahedron is really forming this cuboctahedron shape. And we've seen this cuboctahedron before because it is the sort of polytope which is formed by the root system of the A3 lattice. So this is sort of sitting right in the middle of the A3 lattice. And there's actually more going on in this picture because if you imagine drawing vectors from this black ball to the other colored balls, you're going to get three vectors pointing out, and they're forming this sort of basis of the root system of the A3 lattice. And then there's this sort of symmetry-based way of building everything out. But the way I like to think of the cuboctahedron, maybe like the simplest way I know to think of it, is if you get a cube, like this red cube here, and then you mark each of the edge midpoints, and then you cut the corners off the cube through those edge midpoints, the cuboctahedron is what you get. And you can see that that's also evident from this sort of view of the thing as this sort of intersection of this cube and this kind of dual octahedron here. And so now if you take another look at this shape, wherever you see two black dashed lines that are crossing each other, you can think of that as like an edge midpoint of the cube, and you can think of that as like a vertex of the cuboctahedron. So I'm not drawing the cuboctahedron, but if I was, then for each of the sort of 12 edge midpoints of the cube, for example, here and here and so on, you'd have a vertex there. But you can see that these long black lines are passing through exactly those points. And what are these long black lines? Well, they are the lines which are sort of perpendicular to the planes which formed this spherical triangle here, which we started with. From this Coxeter view, we started with this spherical triangle here, and then we reflected it around. And that's how we built things out. But instead of that, we could start with that spherical triangle, but if we want to go onto the other track, the sort of lattice-centered track, then we start with our spherical triangle and our planes and so on, but then we, instead of having those planes, we replace those planes with these perpendicular vectors. And then we have these three perpendicular vectors. And those vectors correspond to the vectors that we saw earlier. They're the three basis vectors of the root system of the A3 lattice. So that's the kind of structure that we were picturing here. And what did we do with this structure? Well, we had these three vectors, and then we started looking at planes perpendicular to those. Well, we just saw what they are. We kind of got those up front with the Coxeter view, but we look at those planes perpendicular, and then we start reflecting things, which is just what Coxeter does. So you can see now, hopefully, that these two approaches are locking together. And also, I personally am quite blown away by the richness and the beauty of this geometry. By thinking about this sort of symmetry and just starting with this fundamental region here, this triangle, and reflecting it around, we're getting tetrahedra, dual tetrahedra, stellar octangular, cubes, octahedra, cuboctahedra, rhombic dodecahedron. The relationship between these things is so lovely, and it all just is tied together in such a pleasant way. You know, it's one of those lovely parts of mathematics where if someone just explains a bit of the story, it might seem kind of complicated, but there's a certain point beyond which the more you know, the more sense it makes and it gets simpler again. But the real point, just to finish the story, is that if we imagine our original tetrahedron, and then we imagine what happens when we reflect it around using these different planes, these three different planes, that's going to change our tetrahedron. Sometimes we'll have a sort of mirror image of it. And if we reflect it a couple of times, we can get like a rotated version of it. But we can get all of the symmetries of the tetrahedron by looking at things this way. So not just the rotational symmetries, but also the symmetries which change things into mirror images. Then we have S4, which is our symmetric group, because the tetrahedron has 4 vertices that every vertex looks similar to every other vertex, and it's highly symmetric. So we have this connection with our symmetric group here, our group of permutations. Okay, then, so we've seen the A2 lattice, and we've seen the A3 lattice. Now, what about the more general case? So it turns out that this story goes on and on into higher dimensions. There's an A4 lattice in 4-dimensional space and an A5 lattice and so on. So more generally, we can speak about the AN lattice, where n is some integer that's greater than 1. Integers just means whole number. So we want to understand what these lattices are more generally. And it turns out that algebraically, it's actually very easy to understand what these AN lattices are. They have a remarkably simple sort of form. But we also want to understand what these things are geometrically. And so we're going to use a little bit of mathematics involving vectors. When mathematicians are talking about one-dimensional space, they typically think of this as what they'll write as R. And what they mean there is the real numbers. So the idea is basically that if you have a line, then you can think of every point on that line as a number. And they talk about real numbers, which means that they're including fractions and also irrational things like pi and so on. So you can basically visualize R as an infinitely long line. And it has points on it, like 7 would be a point in R. So we could say that 7 is in R. So this symbol here just means in. So what about if we want to talk about 2-dimensional space? Well, in this case, we imagine that there are 2 lines that are perpendicular and they cross at the origin, which we call 0, 0. And then if we have a general point on this plane that we now have, like for example here, well, that point's going to be, let's say, x across and y up. So x and y are going to be the coordinates of that point. And you can see that this point on the plane is described by 2 numbers, as are all points on the plane. And so we write r squared to denote the plane, because the points on the plane consist of pairs of real numbers. And similarly, if we have a point in 3D space, you can describe that point with 3 numbers, you know, how far across you have to go, how far to the right do you have to go, and how far up do you have to go, x, y, and z. And so you need 3 numbers to describe a point in 3D space. So we write 3D space as r to the power of 3. And similarly, 4-dimensional space would be r to the power of 4. We can sort of make models of it, but it gets harder to visualize. But this is the basic idea. So when we're talking about n-dimensional space, we write this as r to the power of n, and a point in n-dimensional space is going to be something like this. So we write it as x1, x2, comma, dot, 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 comma, xn. These things here, x1, x2, and so on, are just going to be real numbers. And if we have n of them together, they are our coordinates, and we have a point in n-dimensional space. So this is really lovely because, you know, even if we have difficulty visualizing these things in higher dimensional space, we can still talk about them completely exactly using all this algebra. So I want to give you a flavor of what this AN lattice is. It's going to basically be a set of points in n-dimensional space. And I want to express how we can think about this because it's very, very interesting. To get into this subject, we're going to need to know about a couple of operations that we can do. So let's start by thinking about 3-dimensional space. So this corresponds to a point in 3-dimensional space. And there's an important operation that we can do on these points, which is to add them together. Now, the way that we do that is we just think about these things as being like numbers, but they're sort of like three-dimensional numbers. So to add them together, we just add the first coordinates together and we get 8. And then adding the second coordinates of each point gives us 11, and so on. And then the way that we can think about this geometrically is like this. So we have our points in 3D space. So for example, 1, 3, 2. To get to this point, we can go one step along the x-axis, and then we can go 3 steps in the direction of the y-axis, and 2 steps in the direction of the z-axis. And then that journey that we've taken is sort of indicated by this purple arrow here, and we call that a vector. And you see it's pointing out of the origin, 0, 0, 0. And so we can also think of those points 1, 3, 2 as corresponding to this vector. A vector means arrow, right? So similarly, we have another vector for 7, 8, 9. And then to visualize what it means to add these 2 points, imagine we sort of get this purple arrow here, and then we slide it along our brown arrow. So we sort of slide this purple arrow, keep it pointing in the same direction, but slide it along here. So it ends up pointing out of here. And that's going to point to a new place in 3D space. That's going to have coordinates 8, 11, 11. So geometrically, adding these points / vectors just corresponds to sort of putting the vectors end to end and seeing what big vector that makes. And then the other operation that we're going to need to know about is dot product. I'm just going to give you a sort of algebraic description of the dot product for now. I want to get into the geometry of this later, but the basic idea is that we just times together their first coordinates. That gives 1 times 7 in this case. Then we times together their second coordinates. That gives 3 times 8. And times together their third coordinates. And then we just add those numbers together. In this case, we get 49. So in some sense, this is measuring sort of how much of these vectors are parallel to one another. But we'll get into the details of what the dot product means later. I should also say that this kind of dot product, this is what most people are familiar with. And this comes from Euclidean geometry, Euclidean space. But we're going to see later that it's actually quite helpful to think about other kinds of dot products in more general situations. But that's enough machinery. Now we can define what this AN lattice is. The first thing I want to say is that this AN lattice is a subset of n-dimensional space. So this symbol here means subset of. In other words, every point of the AN lattice is a point of n-dimensional space. But actually, this is a bit of a controversial thing to say. What I really want to say here is that the AN lattice is n-dimensional. I mean, we've already seen A2 was this 2-dimensional triangular lattice. I showed you this model of A3, and so it makes sense. But actually, people like to think of AN as living in a space of 1 dimension higher. This is a funny thing. You don't have to do that, but it makes the algebra a lot simpler. Of course, you can imagine that n-dimensional space can be thought of as sitting in n+1 dimensional space. Like if I have an x, y, and z coordinate, I'm free to contemplate what happens when the z coordinate is 0. You know, if I always stay on the ground, then you could say I live in a 2-dimensional world, even though like there is a height, but if I never exploit it, then I might as well be in 2D. In a similar way, there are certain patterns in geometry which, even though they might be n-dimensional, it kind of helps to think about them in n+1 dimensional space. So an example is if I draw this picture on this piece of paper. Well, if I have the piece of paper like this, then it's really in 3D space. And, you know, this is a sort of slanted plane. So if you want to describe where that smiley face is, you really want to use an x, y, and a z coordinate. Although, you know, really it is just a 2-dimensional thing. Okay, I tell you that AN should be thought of as living in n+1 dimensional space. So what is it then? Well, here it is. It's the set of points in n+1 dimensional space which have integer coordinates that add to 0. Let's see what this means. For example, if we think about A2, then in this context, we can think of it as having points like with coordinates 5, comma, -4, comma, -1, for example. Or here's another point, 1, -1, 0. You see that these are points in three-dimensional space. As I say, I sort of went one dimension higher than I needed to. So you see that these are points in three-dimensional space, and they have the feature that their coordinates are whole numbers, integers, and that if we add these three numbers in the coordinates, we get 0. And so A2 can be thought of as the set of all points like this. Now, this is a bit confusing, right? I said that A2 is really a two-dimensional thing. I mean, we saw it. It's the triangular lattice. So why are we now thinking of the points of A2 as being in three-dimensional space? Well, the short answer is that there's a certain plane in three-dimensional space that all of these points lie on. I'm going to show you a visualization of that shortly. And since A2 is contained within that plane, it is effectively two-dimensional. And actually, we can really make it properly two-dimensional. I want to show you how to do that. So if you'll believe me, then this is a description of A2. And this is a description of AN more generally. This is A2. This is our triangular lattice. But remember, the way that we approached A2 was that actually what we started with were these 6 root vectors. If you remember, we had this point in the middle, and then we had these 6 vectors pointing out of this origin. And so they gave us these 6 points, and then we could combine those vectors to fill out the rest of this triangular lattice. So these 6 vectors form something called the root system of A2. And so how does this work more generally? Well, more generally, if we want to get the root system of AN, then we can look at all of the points of this kind of form, the points that have one of their coordinates equal to -1, another one of their coordinates equal to 1, and the other coordinates equal to 0. So these are points in n+1 dimensional space. And so, we're looking at all the permutations, so the ways that we can swap things around. So 0, 0, 1, -1, and then a load of zeros. That's going to be another point of this root system. If we can understand what this kind of set looks like in general, then we're going to be done, because we can build all the other points of AN starting from here. And I like to start from here because it reveals a lot of nice geometry. So I'm aware that there's a lot of new ideas suddenly coming in here. So let's look at an example. Let's take a look at A2. A2 consists of these 6 points, and these are points in 3D space. We say, okay, this is a subset of r to the power of 3. I think this is going to be much clearer once we visualize this stuff. Let's go to GeoGebra and take a look. Here are our 6 points here. And you can see that they're all lying in three-dimensional space, yes, but there's also 6 of them forming this kind of hexagonal shape. And you can see that they're really confined to this sort of plane here. And this is the plane consisting of all of the points in 3D space that have their coordinates adding up to 0. I mean, you can see clearly these 6 points all have that feature. And the set of all points with that feature forms a two-dimensional plane. And really, we can think of our A3 lattice as living in this plane. In fact, the A3 lattice consists of all of the points on this plane, which have their coordinates adding up to 0. And this is the sort of root system. And so if we also look at the origin here, this point 0, 0, 0, then of course that also lies on this plane, and we can proceed as we did at the beginning of this video. We can draw arrows out from the origin to these points, and we can do all sorts of things. But personally, I find this situation a little bit annoying geometrically. I mean, AN really is an n-dimensional thing, but we're putting it in n+1 dimensional space. That feels a bit wrong. So how can we actually transform this lattice to make it really lie on the plane? Well, the way I like to think of it is we have this gray plane here where z equals 0, and we have this blue plane where our lattice naturally lives on. And we really want to sort of move our lattice onto this gray plane. If you imagine there's an angle between the grey plane and the blue plane. And if we sort of bisected that angle, cut it in half with another plane, then we could reflect in that new plane that we've added, and then that would reflect everything down onto the grey plane. So let me show you how this works. It works quite nicely. Firstly, we have this light blue plane. Now, how can we describe that more precisely? Well, here's the way I like to think of it. So what I've done is I've added a new point called 1, 1, 1, and I've made a vector pointing at that. And I've colored that vector blue because you can see that our blue plane is really the plane that's sort of perpendicular to that vector. You see that? So that's kind of interesting. And also I've added this other vector pointing at 0, 0, 1. And so what I want to do now is to bisect these vectors. I'm not going to get into what that means. Basically, it means finding a vector that's sort of pointing at halfway between these two. And there's a well-known way to do it. This orange line I've just added bisects the blue vector and the black vector. And so now if we just find the plane that's perpendicular to that, that's going to be what we want, right? Because you can see that this orange plane I've just added is sort of halfway between the blue plane and the grey plane. If we use this to reflect things, then that's going to get us onto the grey plane. So like if we click here and then we reflect, we can do that. We can click here and reflect. We can click here and reflect. We can spin things around so we can get a better look. We can click here and reflect. We can click here and reflect, and so on. And you see now that we're finished because we've pleasantly got these 6 points which are actually lying on the plane now. That's what we wanted. So we've managed to move our root system for A2 from 3-dimensional space down into 2-dimensional space where it belongs. And actually the method that I'm using here generalizes to high-dimensional space. So I wrote this Mathematica worksheet, which has also some pastings from a paper by Heckman. And in this worksheet, I have code and also mathematical description for how to do this sort of moving AN into the n-dimensional space where it belongs more generally. So this is how I obtained pictures like this, for example. They all fell out of this algebra, which is it's really quite pleasant because, you know, we're sort of starting in 4 dimensions and we're doing some kind of crazy reflections in hyperplanes and things. Because, you know, I just showed you a 3D situation where we were reflecting on a plane to get stuff down to the grey plane that we wanted. And basically I had to do the same thing, but 1 dimension higher to get this, because the straightforward description of the A3 lattice is as points in 4D space, but really they're all confined to this sort of 3-dimensional hyperplane where all the coordinates add up to 0, and you can do that sort of reflection thing to get down to what you want. But I should mention that this sort of transformation that I just spoke about is what's called an isometry. That means it preserves all the distances. Like, this is why I wanted to do it using a reflection. I didn't want some sort of transformation which would warp. For example, in the A2 picture, we had a perfect hexagon in that kind of ramp plane. And we wanted to change that to be a perfect hexagon in the z=0 plane. That's what using a reflection did for us. And this works in higher dimensions as well. But really, this is the sort of key idea. This is the definition of the A2 lattice. But you have to sort of believe me that really all these points are confined to an n-dimensional hyperplane. So we really can think of this as something in n-dimensional space. And this is how we would describe the n-dimensional hyperplane that AN's really confined to. It's the set of all points in n+1 dimensional space that have coordinates adding up to 0. Typically, we write the set of integers as z to the power of n+1 is the set of all n+1 tuples of integers. So, you know, where we have like a list of n+1 integers. Now we can write a very succinct description of AN itself. So we can say that AN is equal to this set of points here in n-dimensional space with integer coordinates that all add up to 0. So that's kind of what AN is. But like I say, you're probably better doing a kind of isometry to really make it into n-dimensional space. But maybe you're happy just bearing in mind that it's confined to this n-dimensional hyperplane. I think this is how a lot of mathematicians like to think of it, because obviously, people speak about it this way because it's simpler. Okay, so far I've mostly been talking about these AN lattices. If we have a particular value of n, then a drawing we can make that sort of corresponds to the AN lattice in some way is this AN graph. So it's just a path with n different vertices like this. So this is what we call an AN graph. Now I'll get to the significance of these graphs later, but there's also something called a DN graph. So again, it has n vertices, but the difference now is that it has a sort of fishtail at the end. So for example, D4 looks like that. It's like a path. In this case, it's just a path with sort of one edge. And then at the end, it does a fishtail so that it ends up with n vertices. So these graphs AN or DN, for different integers n, are extremely important for us. And then there's three other graphs that we're especially interested in. This might seem a bit cryptic at the moment, but hopefully in the fullness of time, the reasons why I'm saying this are going to become clear. So this graph here is E6. So E7 is similar, but a bit longer. And then the most beautiful one is E8, which has 8 vertices. It turns out that these graphs are absolutely essential in mathematics. They're called the ADE graphs. So we've been talking about these graphs of the form AN, and I've tried to get across that for every one of those, there's a lattice. The lattice associated with AN is in n-dimensional space. And the same is true for these other structures as well. If we take any ADE graph with n vertices, there's going to be a corresponding lattice. So I want to try and convey what these lattices look like. And so we've spoken at length about these AN lattices. Now let's speak about these DN lattices. So what are they? Well, the easy way to describe what the DN lattice is that it's a subset of n-dimensional space, and it consists of a load of points that have integer coordinates. We could say that it consists of these points x, where each coordinate is taking a value in the integers. And the DN lattice just consists of such points where the sum of the coordinates is an even number. This may remind you of the picture I showed earlier in GeoGebra, where we are marking the different points in the three-dimensional integer space according to whether they're even or odd. And in fact, if you think about it, the D3 graph we could draw like this, and it pretty much looks the same as the A3 graph. And so actually, all the structure that we get for A3 is the same as what we get for D3 in some sense. The output's the same, but the interpretation is a bit different. But sorry, that's a bit tangential. Let me carry on talking about this DN lattice. This is a lattice like before. And so it has a root system. I'm not going to describe the root system directly, but I will tell you that this is a basis for the root system. So these are now unit vectors in n-dimensional space. And this basis looks very similar to the basis that we had for AN, except that there's this extra sort of vector tacked on. And we're actually working at the same dimension as our lattice, not like the weird case with AN where we're working one dimension higher. And so you can see that these basis vectors here are corresponding to these vertices in this DN graph here. And hopefully all this is going to make more sense when we look at it in terms of the population game. But I just want to say that really the story here is very much as before. So we can start off with these basis vectors, and then we can take planes which are perpendicular, hyperplanes which are perpendicular to each basis vector, and we can do reflections in those planes. And then we can take integer combinations, and that's going to fill out the root lattice for us. That's going to give us a polytope. So I should have used that word polytope before now. So when we have something in 2D, that's a polygon. When we have it in 3D, that's a polyhedron, many faces, right, from the Greek. And then the general word is polytope. So when we get things in higher dimensions like hypercubes or this 24 cell, these are polytopes. And if we take one of these ADE graphs, it's going to have this sort of root system, and there's going to be a polytope associated with that. And it's usually a really beautiful one. For example, with D4, that looks like this. And this is an extremely beautiful structure. So D4 itself lives in four-dimensional space, and it corresponds to something called the integer quaternions. And so that's what the whole lattice, the D4 lattice, looks like. But then we have this root system, and the root system actually corresponds to this beautiful 24 cell here. This is one of the most extraordinary shapes in mathematics. This is a regular polytope in 4 dimensions. And so we have our Platonic solids in 3 dimensions. In 4 dimensions, this has an extraordinary place. You might be wondering why we're setting up all this machinery. What are we trying to do exactly? And really, what I want to do is to show you that the beautiful structures that we've seen involving using mirrors carry on into higher dimensions. So you remember the way that we started the A2 pattern was with these 2 vectors here, this red vector and this blue vector, separated by 120 degrees. And then from there, we are able to use this idea of doing reflections in planes perpendicular to our original root vectors to get the rest of the root vectors. And then we could add those together to fill out the whole A2 lattice. And there was a similar story that we saw with this A3 lattice here. There we have these sort of basis vectors, which consist of these 3 ones going from this black central vertex to the red, blue, and green, respectively. And once we have those, we can look at hyperplanes perpendicular to them, we can reflect in them, and we can get the other 9 vectors in this root system of A3 here. Those would be these vertices of our Cuboctahedron. So I'd like to describe how this works more generally now. So more generally, we want to think about this root system of AN. And I've been saying that we can really think of this as this set of permutations of vectors like this that have a 1 and a -1 and zeros everywhere else. So let's call this set the set of roots of AN. Seems like a good name for it. And we want to describe it a little bit more succinctly. So let's introduce a bit of notation. We're going to write EI to denote what I could say is the ith unit vector. So it has a 1 in the ith position and zeros elsewhere. So for example, if we're working in 3-dimensional space, then this is the first coordinate, this is the second, and this is the third. And so E2 has a 1 in the second coordinate and zeros elsewhere. And then E3 is going to be this, and so on. So when we're in n plus 1-dimensional space, we can now describe our set of roots of AN very succinctly. Basically, it's just the set of all vectors we can get by taking an EI and subtracting an EJ, where I is different from J. So basically, this is just a fancy way of saying that we're dealing with these permutations of this kind of thing, because, we have a 1 and a -1 and everything else is zeros. But also using this notation now, we can give a basis for these roots. What I mean by that is we're just going to pick out just a few roots, and they're actually going to be good enough for us to be able to get all the rest of our roots. In particular, when we take this set of vectors here, this is going to form what we can call a basis for our roots of AN. This is a sort of special selection of these roots, and it has 2 very important properties. One of them is that we can form the rest of the roots by adding pairs of things in this set together. So in that sense, it's sort of analogous to, when we pick like a unit vector in the different directions and we can add them together in combinations to make the rest of the points in the space. So that's one thing. But the other thing is that it turns out that this sort of basis works really, really nicely with this idea of reflecting in the hyperplane perpendicular to a vector. This idea of doing reflections turns out to be really central to the whole kind of theory that we're going to be talking about. I'm actually, as time goes on, I start to feel like the idea of reflection in geometry is more and more fundamental. And I'm starting to think that, it might be that a vast number of things in geometry are best thought of primarily in terms of reflections. For example, rotations. Like if you want to rotate something about, say, an axis, you can do that by doing two reflections. So reflection, in my opinion, is more primary than rotation. Okay, so as time goes on, I realized that this is one of the most important formulas in geometry because it tells you how to reflect a vector in a hyperplane. And it turns out that many of the things that you do in geometry, lots of these rigid motions like rotations and such, can be described completely in terms of these sort of reflections. And reflections have a lot of nice properties. I mean, you can see that a lot of this theory involving ADE lattices can be described very pleasantly in terms of rotations. So I want to try to explain this formula a little bit. I want to give you a sort of flavor of why it's true. Let's just begin with the setup. We have n-dimensional space, and we have this vector v. And that's what we're going to use to do some reflections. How do we do that? Well, we take v, and then we take the hyperplane, which is perpendicular to v. Now, if that boggles your brain, if you're thinking, oh, I don't know what a hyperplane perpendicular to a vector in 56 dimensions looks like, well, you're not alone. It turns out that we're only going to actually have to think about a two-dimensional scenario to understand what's going on here. So let me start saying again, we have this vector v, and then we have this hyperplane that I'm going to write as vperp. We can think of vperp as the set of all vectors y that are perpendicular to v, in the sense that the dot product of y with v is 0. I'm going to revisit the dot product momentarily, so we'll understand more about what this dot product really means. We have this expression here for this hyperplane, which could be high dimensional, difficult to visualize, etc. But actually, we're going to use it in a fairly limited way. We're going to suppose that we have some vector x in our n-dimensional space. And what we want to compute is this expression here. Now, what this is, geometrically, is it is the reflection of the vector x in the hyperplane that's perpendicular to v. Now, here's an important thing to realize. We have these vectors v and x. And then what we want to do is sort of reflect x in this hyperplane perpendicular to v. You can see in this picture, I'm reflecting x in this, and I'm getting this. Well, the point is that v and x are just vectors. And so there's going to be a two-dimensional plane that's spanned by those vectors. And we can just think about what's happening in that two-dimensional plane. So even though we might be in n-dimensional space, you can look at a picture like this, and you can assure yourself that actually I only have to focus on this two-dimensional plane. And so if you just sort of draw this plane that contains x and v, this is going to run into this hyperplane vperp somewhere, but it's going to intersect our plane of interest at a line. And so we're essentially just reflecting x within this line here, this dotted purple line. This is what we're interested in. And now I say that there's a formula for this result, and it is this formula. Basically, the way that you can think about this is as follows. This is our vector x, take away psi, take away psi. And what is psi? Well, algebraically, it's this quantity here, and geometrically, we can think of it as the projection of x onto v. So if we project this vector x onto this vector v, we get psi. So that's what it is. And I claim that psi is given by this expression here that I just circled in red. So let's try and justify this a little bit. So we're going to go sort of back to basics. Here's our vector x. So it has these different components, x1, x2, etc. And here's our vector y. So their dot product, let's define it algebraically to just be x1 times y1 plus x2 times y2 all the way up to xn times yn. We add all that up and we call it the dot product. Now I'm going to get on to how we can think of that geometrically later. I should also add a note here. I'm talking about the Euclidean case. Okay, this idea of this dot product is actually really magical because we can talk about how it's working in the Euclidean case, as I'm going to for the next few minutes, but we can also sort of generalize all of this story. In fact, we might have need to do so later. And that gives us a very powerful and relatively easy way to start thinking about non-Euclidean situations where distances and so on work differently to in the world we're used to. So in a sense, this dot product is really allowing us to think about distances and metrical notions within our linear algebra. And we're just going to stick with the Euclidean case for now. The next thing is, what do we get when we take a vector x and we dot it with itself? So what is x dot x? Well, we can figure it out using our formula. And it's just the sum of the squares of the coordinates of x. Sometimes this is called the quadrant of x. Actually, better to say that the quadrant of x is defined to be x dot x, because that's true even if our dot products might be working differently in some sort of non-Euclidean situation. Anyway, we're not thinking about that. But another way you can think about this quantity is it's the length of x squared. So when I write x with these vertical lines, that means the length of x. And so another way you could say this is that the length of x is the square root of the quadrants, or it's the square root of this sum of squares. So you can think about this as really being a kind of consequence of Pythagoras' theorem, but working in n-dimensional space. Like in 2D, Pythagoras' theorem is saying, well, if you square this and add it to the square of this, you get the square of this, which is the distance from here to here. But that formula sort of generalizes to higher dimensions. And then, to work out a distance in 3D, you want to be looking at the displacement in the x-coordinate, squaring it, take the displacement of the y-coordinate, square it, take the displacement of the z-coordinate, square it, add those up, and then square root them, and so on. So, okay, now we understand how to take the dot product of two vectors and how to figure out the length of a vector. So, okay, now I want to define another quantity, and I'm going to call it the normalization of our vector x. So basically, we just get our vector x, and then we divide by the length of x. And that results in a vector that points in the same direction, but it only has a length of 1. And we call that vector x hat. Okay, so we take our vector x, we normalize it by dividing it by its length, and we get the normalized version, which we call x hat. So you can see how we can sort of picture this here. We have our unit circle consisting of all the points a distance 1 from the origin. And then we kind of see where this vector x pokes through the unit circle, and that gives us x hat. Okay, so there's something else that I want to define. I'm sure many of you know about this, but I don't like making videos where I don't define non-trivial concepts. So I want to tell you about the cosine of an angle. Okay, so what's going on here? Well, so I think a good way to explain this is as follows, right? Let's suppose that we have our unit circle, this black circle, all of these points, distance 1 from the origin. And then we're going to get a particle. It's going to start here on the circle, and it's going to move around the circle at a uniform rate. And what we're going to do is we're going to look at how far away that particle is to the right of the origin. And we're going to plot that as a function of time. And then what we're going to see is a plot a little bit like this. So when we have time 0, our particle is going to be at a displacement 1 away from the origin to the right. And then a little bit later, the horizontal displacement is going to be a little bit less. Eventually, at a certain time, the displacement horizontally is going to be 0. And so basically, if we think of our angle theta as time, because our particles going around this circle at a uniform rate. Let's say it takes 360 seconds, for example, for this particle to go all the way around. Well, then the time is going to be the same as the angle. And if we plot this sort of horizontal displacement of our particle over time, then we're going to get this plot of our cosine graph. To say it a bit more geometrically, if we feed in the angle pointing from our origin to our particle, our angle is theta, then cosine theta is going to give us the sort of x coordinate of our particle, or I'm calling it x1 in this case. So I write x1 equals cosine theta, where this particle is at coordinates x1, comma x2. There's a question here about what you want to measure angles in. Do you want to measure them in degrees so that when this theta gets to 360, it sort of resets to 0? Or do you want to work in radians? So we say there's 360 degrees in a circle, or there's 2 pi radians. As I get older, I kind of feel more and more that it's a bit weird that people like to measure angles in radians. But anyway, let's carry on. But anyway, we're not really going to do any computations with this stuff. So I'm not going to worry too much about whether we're working in radians or degrees. So just before I circle back round to thinking about dot products and reflections and so on, I just want to notice something else about this little diagram. So this is our vector x here, and we have this other vector here. I could just call it 1, 0. Okay, so it's just this horizontal vector. Well, can you see that the value of cosine theta is, in a sense, measuring how parallel x is to our vector 1, 0, right? Like when theta is 0, x and 1, 0 are lying completely on top of each other, and cosine theta is as big as it can be. It's 1. And then as the angle increases, when the angle gets to 90 degrees or pi over 2 radians, then cosine of theta is going to be 0. And in that case, these two vectors are totally perpendicular, and it carries on. X is then actually pointing in the opposite direction to 1, 0, and so on. So cosine theta is really, in a sense, measuring how parallel these two unit length vectors are. And so it turns out that the same situation holds more generally. If we have two vectors, x hat and y hat, and they both have length 1, and we look at the angle between them, then in a sense that's telling us how parallel x hat and y hat are. Okay, and actually it turns out that the dot product of x hat and y hat is cosine theta, where theta is the angle between them. So I'm not going to prove this, but hopefully it makes some intuitive sense to you. Like, you can take this picture I'm showing here and kind of rotate it in your mind so that, x becomes horizontal, then it looks like the previous picture. And so there you go. And now, actually, what we can do is we can take this formula, if we believe it. I mean, I haven't really proved it, but if we take it for granted, then we can rearrange this to get the famous formula that sort of relates the cosine of an angle between two vectors with their dot product. So this is an important formula in linear algebra, and we're going to get it now. If you take a look at this picture, you can see what's going on. We start with two general vectors, x and y, and then we're going to normalize them. So we get x hat and y hat, and we get those just by dividing by the lengths of the original vectors. And so if we believe this formula here, x hat dot y hat is cosine theta, well, then we can just substitute our expressions in for x hat and y hat, and we get this. And then if we rearrange this, we get the familiar formula that tells us the dot product of x and y in terms of the lengths of x and y and this angle theta between these two vectors. So, okay, with all this under our belts, we can return to this problem of obtaining this formula here for reflections. Like I say, I want to define psi here to be the projection of this vector x onto v. Then hopefully you can kind of see that if we take this vector x and we subtract psi and we subtract psi again, then we're going to get the reflection of x in this line here. And we could alternatively say we're reflecting in a hyperplane, but we're just looking at this two-dimensional slice. It's actually, I think, for a first glance, better to just think about this as a picture that's purely happening in 2 dimensions. So if we believe all that, then the result we get when we reflect x in this hyperplane should be x take away 2 psi. And so we hope that psi is equal to this, because then this would indeed be x take away 2 psi. So this is the formula that we just need to prove now. Basically, we can just define x kind of geometrically as saying, well, it's the projection of x onto v. And we want to see if we can obtain this formula here for it. So this is the situation that we want to contemplate. I'm going to draw a picture that's a bit regular. So let's just redraw it like this. So we want to get a formula for psi. So psi is a vector. And the way that we can sort of think about psi geometrically is if we have these kind of rays of light coming in perpendicular to V, then psi is kind of like the shadow that X would cast on this vector V. But a more exact way to think of it is as follows. We know that psi is parallel to our vector V. Okay, so that means that if we take V, then we should be able to times it by some scalar. We should be able to rescale it and make it into psi. So another way to say this is if we take our vector V and we normalize it, so we get V hat, and then we times that by some number K, well, we should be able to find some number K such that that results in psi. Okay, so we take our V, we normalize it, and then we scale it by K, and we get psi. And that number K that we need to use should actually just be the length of psi, right? So we take our vector V, we normalize it, then we times it by the length of psi. That should give us psi, okay? So we could say that psi is K times V hat, and K is just the length of psi. So this is nice because now we can draw a picture like this. There's going to be an angle theta between X and V. And if we just think about lengths, well, we know that it's a length of K down here on the adjacent length, and there's a length here on the hypotenuse, which is the length of X. And so we can use our trigonometry, right? Cosine theta is the adjacent divided by the hypotenuse. If you're unfamiliar with this, you can Google the definition of cosine because it's really the sort of definition of cosine theta. And so basically this formula gives us this. Cosine theta is K over X. We can rearrange it to get our formula for K here. And so now we're basically done. We have to just do a little bit of algebraic tidying up and we're going to get to our formula. So let's now return to our problem of calculating psi. Well, we've said that psi is K times this normalized vector V. And now we have our formula for K, which we can substitute in. And we also have a formula for cosine theta. So remember, the cosine of the angle between X and V is basically just the dot product of the normalized version of X with the normalized version of V. So we have this formula as well. So we can substitute that in for cosine theta. And so now we have this. And then we expand out what X hat and V hat really are, like so. So now we're going to use another property of the dot product, which is basically that if we have two vectors, X and Y, and let's say we take X and we rescale it by multiplying it by some number R, and then we dot that with Y, well, the result is just the rescaled version of X dot Y. So we can sort of pull scalars outside of the dot product. And we're kind of using that within this algebra here. We're expanding out this to this and so on. And then we're sort of doing some tidying up, cancelling these lengths of X, bringing this inside here. And then we get this expression. And then, you know, what's on the denominator? Well, it's the length of V squared, which is the same thing as V dot V. And we're done, right? We've got that psi is equal to this, right? So this is psi. So X take away 2 psi is this. And you can see that this is now making sense with our kind of intuition about how we can sort of reflect X in this mirror, which is VPERP, right? So we sort of look how far the tip of X is away from our mirror, and then that's psi, and then we add that displacement again, and then we get this sort of mirror image of X in this mirror VPERP. And here we have this beautiful formula which tells us what this vector is when we sort of reflect X in this hyperplane here. So why do we care about this stuff? Well, let's go back to our basis here. So we give these we can give these vectors names. This is B1, let's say, and this is B2, and this is Bm. So these are our sort of basis vectors for our roots. And so now what I want to do is to go back to the original picture that we started with. We had our origin here, and we had B1, and then at an angle of 120 degrees, we had B2. So here our origin is 0. So let's try and remember what we did. So we drew this hyperplane here that's perpendicular to B2. So we can call this B2 perp. And then what we did is we reflected B1 in this hyperplane. So the result is called S B2 perp of B1. Because we're reflecting the vector B1 in the hyperplane that's in this hyperplane B2 perp. I mean, I say hyperplane, it's a line, but you know. So, okay, let's carry on. There's going to be our hyperplane perpendicular to the red one. And so this is the hyperplane B1 perp. And if we reflect this vector in B1 perp, then we get this one. Well, we would if I'd drawn it properly. SB1 perp of SB2 perp of B1. And here's the hyperplane perpendicular to our green vector, or it would be if I was drawing this properly. Maybe I'll just redraw it a bit like that. I think that looks better. And then we're going to have this blue vector here. And so I'm going to call this green vector G. So then we can call this G perp. And this is going to be S G perp of B1 because it's reflecting B1 in this hyperplane here. And then finally, we can say, well, what we're doing here is reflecting in the B1 perp hyperplane this thing here, which is SG perp of B1. So you can see that we can really use this idea of reflections to fill out our root lattice. But it's even nicer than that, because what I've done here, I sort of started with B1 and B2 and used this idea of reflecting in these perpendicular hyperplanes to fill out the root lattice. And the same thing can be done in higher dimensions. But also look at this. If we take this vector here, which is B1, and then we add B2 like this, then we get G. So we can also write this as B1 plus B2. And we can also write this here, you see, as minus B1, because it's just like B1, but it goes in the opposite direction. And this is minus B2. And this is minus B1 minus B2. So we have two different ways to look at it. Like we can really think of these as sort of basis vectors. And if you like, if we think about things in terms of those basis vectors, rather than our usual sort of perpendicular basis vectors, then we can actually write these different points using that sort of notation, right? So we could sort of write this as saying this is 1, 0. So it's one copy of B1 and 0 copies of B2. And this is 0, 1. And this is 1 B1 and 1 B2. So it's 1, 1. And this is minus 1, minus 1, minus 1, 0, and 0, minus 1. And this sort of graph is like a diagrammatic notation that really kind of corresponds to our lattice. We're going to understand more about this as time goes on. But these different vertices, these n vertices, these really correspond to our basis vectors of our root system. So like this is B1, this is B2, this is B3, and so on when we're working in higher dimensional space. And then in Norman Wildberger's approach to this, his sort of mutation game deals with these population vectors. And these basically correspond to these orange vectors here. They're telling us how these points can be written as combinations of our basic vectors, our unit populations. And then when we do a mutation at the ith vertex, that corresponds to doing this operation where we reflect in the ith hyperplane. And so you can see that this is going to change a vector to a vector, or in terms of Norman Wildberger's population game, it turns a sort of population to another population. There's really an absolutely beautiful correspondence here. And the whole thing generalizes. I encourage you to think about the A3 case. And also, if you're feeling strong, you can look at the A4 case. Now, this is a subject where there's a coalescence of an enormous number of different ideas. I tend to find talking with the AI, I use Perplexity, and I type with it. and it helps me to understand, how these things are related. So I could ask something like, how is the A2 lattice related to the face-centered cubic lattice, or Wildberger's mutation games, or whatever? And I tend to find that that's a really good way to get into this subject, because perplexity in particular is really good at giving references and things that one can follow and really understand more of what's going on. Okay then, so let's make some more progress. I've spoken quite a lot about these AN lattices, but now I want to say something a bit more general, because it's going to be very useful to us. So I say that associated with each of these ADE graphs, we have a root system. So what is a root system? Well, a root system satisfies these properties. It satisfies the property that if we do the dot product of any member of the root system with itself, we get a value which is constant. In our case, this is going to be 2. By the way, I'm talking about something called a simply laced root system in this case. And also, if we reflect in a hyperplane perpendicular to any of the members of the root system, we get another member of the root system. And finally, if we take a couple of vectors u and v in this root system, and then we do the reflection of u in the hyperplane perpendicular to v, then we get u take away some integer multiple of v. There's going to exist this integer k such that the result of doing this reflection is u take away k times v. And we saw that with the earlier examples, right? That if we did a reflection in one of these members of this root system, we ended up being able to build that through integer combinations of other vectors. So we saw that here, for example. So if we want to reflect b1 in the hyperplane perpendicular to b2, then we get this vector here. But we see that this vector here could also be obtained by taking b2 itself and then subtracting some combination of b1, in fact, 1b1 in this case. So we can see this here, for example. So if we're reflecting b1 in the hyperplane perpendicular to b2, then we can get the result by taking b1 and removing some integer number of b2s from it. So the vector defining the hyperplane you're reflecting in is the one that you want to be subtracting some integer number of values of to simulate the effect. That's a little cryptic, but I thought I'd just show you this definition of root system. If we pick a particular ADE graph, for example, this one here, let's say I just picked one at random, then let's make some definitions. So we'll say a population vector is just where we associate every one of these vertices with an integer. Actually, let's take this ADE graph here, A3, because we've already studied this quite a lot. So here's a population vector, 5, 7, -1. Now, the way you can think of this is that actually each of these vertices is getting associated with one of these basis vectors from our root system. So these are B1, B2, and B3. When we write this kind of structure, you should think of this really as 5 times B1 plus 7 times B2 minus 1 times B3. And so you can think of this as a point in the lattice. But now we're having an alternative way to think about it, a simpler way to think about it. We're just thinking of it as associating every vertex in this ADE graph with an integer. And we have a sort of cartoonish way to imagine this. This is a marvelous story way of thinking about this that Norman Wildberger came up with, which is to say that let's imagine that each of these vertices is a city on Mars. And Martians have 3 strange properties. One of them is that there are anti-Martians. So the population associated with a city can be negative. So there are Martians and anti-Martians. If they're in the same city, they cancel each other out. So the populations of cities on Mars are not just natural numbers like they are on Earth. They are integers. They can be negative. The second property is that sometimes there are these events where Martians turn into anti-Martians and anti-Martians turn into Martians. We call those events flips. So sometimes a city flips and then its population basically becomes -1 times what it was before. And the third thing is that in some situations, these Martians can clone themselves, and they can also travel along these roads sometimes, which are connecting different cities. The way the population game works then is like this. We have some population vector, so some association of populations to every city. And then we can choose how we update the system. So we can choose which city we wish to update. So let's say we update this city here. So what happens when we do such a mutation? Well, what happens is that firstly, we make the population of our city negative, so it becomes -7. And then all of the neighboring cities respond to this by cloning their populations and sending these new clones along the roads into the old city. The resulting population here in the middle is going to be -7 plus 5 minus 1, which is -3. And then the populations of the first city and the third city are unchanged. This is the result of updating this population vector here at this central vertex here. But it's a little bit like a game of Sudoku or something. We can make any moves in any places that we like and alter the game accordingly. Basically, what we do in the population game, we start off with what we call unit vectors. So a unit vector is just going to be a population where we have a 1 at one of the cities and no other Martians at any other city. And we start at one of these unit vectors, and then we do any combination of mutations at any of these vertices. And it turns out that what we get by doing that, we call it a root population. And if we look at all of the root populations that we have, so all of the population vectors that we can get by starting with a unit population vector and doing some sequence of mutations, that turns out to exactly be corresponding to the root systems that I've already discussed. Now, the reason that this happens is absolutely beautiful. So the point here is what I've spelled out here, and this really connects everything together in a very lovely way. Here's the idea. We have our ADE graph. Let's do A6 for a change. And so each of these vertices is going to get associated with a sort of unit population vector. Let's number these vertices. And then if we pick a particular vertex, let's say this one, there's going to be this vector B2. And this is going to be a unit population vector. There's a population of 1 at city 2 and populations of 0 elsewhere. So this is going to be what B2 looks like. And I want you to think of this as corresponding to something in the root lattice. So here's how this works. You remember that we were dealing with a geometric system where we had these points in n-dimensional space, and we're really working with Euclidean space. We just had an ordinary dot product. Okay, so now we come to the central result, which really connects everything together in a really beautiful way. Suppose we have one of these ADE graphs, and it has n vertices. So for example, we might be thinking about A3. This has these 3 vertices. I'll write them as 1, 2, and 3. And so in terms of the geometry, we know that there are these different members of the root system, the sort of basis of the root system. So for example, we have B1, which is 1, 0, 0, and B2, 0, 1, 0. And so we have an interpretation of these things geometrically, right? Geometrically, these different coordinates just correspond to members of our basis for our root system. And we know about all sorts of things we can do with these things involving dot products and reflections and so forth. But now, just put all that aside and think about the population game. So the population game is played on population vectors. Those are length n sequences of integers. And so we have this space, this n-dimensional integer space, and we're going to define a dot product on that space. We're not going to take the normal Euclidean dot product that we've been using so far. We're going to define a new one. And here's how it's defined. If we take a unit population vector, so something like this, for example, now we're thinking of these as population vectors. So this would be 1 Martian in the first city and 0 Martians in the others. Well, if we take a unit population vector and we dot it with itself, then we get 2. So I'm writing this new dot product as star. So I'm saying BI dotted with itself always gives 2. And then the other thing is that if we take 2 of these unit population vectors that are different, then we dot those together. So we do BI star BJ, then the result's going to be -1 if I and j are adjacent and 0 otherwise. So why are we setting things up like this? because this is exactly how the Euclidean dot product works when we're looking at the root system in terms of the original space. Okay, so basically, Wildberger's mutation game is looking at the geometric situation and looking at these sort of root vectors, which are really the key thing controlling everything, and then taking the way that they dot with each other as primary. Instead of all of this geometry and how things are laid out, etc., etc., now we just say, okay, we just have a load of root vectors, and then we define the dot product to work as it should work, as it does work in all the situations, and then we can just study it from there. And this mutation game works exactly like that, but much, much better than that. We have this result. And so what this is saying is that when we take our population vector and we do a mutation at the ith vertex, then that just corresponds to doing this sort of symmetry operation. So in terms of Wildberger's space, which is going to be n-dimensional, n is the number of vertices, and it has this dot product, well, we can ask, what does it mean to do a reflection in the hyperplane, which is perpendicular to this unit vector bi? And when we do that on P, then we get this as the result. So this is just the standard formula for reflecting P in the hyperplane perpendicular to bi. However, we're using this sort of custom dot product, but hey, that's defined to work properly for these unit vectors. So this is such a beautiful setup, and we can use it to study all of these lattice structures in such an easy way. Okay, so we've had a very good look at these AN lattices. Now let's take a look at these DN lattices. So these are 4 different kinds of graphs, and they give us different kinds of lattices. And I'm a big fan of these structures because one of them, the D4 lattice, is closely related to this shape here, which is the 24 cell, one of the most beautiful shapes in maths. I'll say more about this later. So one of the beauties of this structure is that there's so many ways to look at it. For example, if we want to look at the D3 lattice, we could say, okay, that's the set of points in 3D space that have integer coordinates, but those coordinates have to sum up to an even number. And so if you think about it, the origin is going to be included within that. And together with the origin, we're going to be sort of including every other point on the plane, a little bit like a sort of 3D checkerboard. And if you think about it, that's going to end up constituting the black and green vertices shown here. So if you imagine that the whole of 3D space is filled with these length 2 cubes, well, then we're basically selecting the vertices and the face centers of those cubes. So we're actually seeing, again, our friend, the face-centered cubic lattice. So it's really quite remarkable that basically the D3 lattice and the A3 lattice that we've already studied are kind of the same thing. But that's not true more generally. Okay, so more generally, for higher n, we have DN lattices and AN lattices, and they're different. Okay, it's just a bit of a coincidence that happens in 3 dimensions here. And so sort of more generally, I'm describing a lot of features of the DN lattice here. I'm going to get into the particular example of the D4 lattice, which I think is especially important for reality. But in general, these are the sort of descriptions. We'll use this notation EI for the ith unit vector in n-dimensional space, right? So like E2, for example, has a 1 in the second coordinate and zeros elsewhere. And now we can describe what the roots are of the DN lattice. And so you can think of these as the sort of points of the DN lattice that are as close to 0 as possible without being 0. And here they are. In terms of being vectors, they're 0 everywhere except for 2 entries. And those entries might be +1 or -1. That's a nice way to describe what these roots are. Guess what shape we get when n equals 4? Then these roots, these roots always form the vertices of a polytope. And guess what polytope they form when n equals 4? Well, it's a 4-dimensional polytope, very special polytope. Yeah, it's a 24 cell. Remarkable thing. Now we want to connect this geometric viewpoint with this combinatorial viewpoint involving these mutation games. And in that way, we can relate Dn to one of these graphs. And it's a graph which has this sort of form. So it has n vertices, and they're almost all in a path, except there's a sort of fork or fishtail at the end. So you can think of the Dn graph as being like a very long kind of capital Y-shaped graph that just sort of forks off just before the end. And then the vertices of this graph, they correspond to these different vectors that are forming a sort of basis for this root system of Dn. So you can see that these are particular vertices within this sort of root system of Dn. And we can use these vectors here to get the other vectors in the root lattice. It's the same kind of thing that happened in the AN lattice. We get these things, we get the hyperplanes that are perpendicular to them, then we start reflecting vectors in this set in these hyperplanes, and we get all the combinations of these vectors, and we end up filling everything out. And this corresponds to playing the mutation game. And so if we wanted to approach this combinatorially, for example, we could look at the example of the D4 lattice. And so this D4 case is a very sort of symmetric case. And so we have this sort of graph, you know, with a vertex in the middle connected to three other ones. And then we can see what happens when we play the mutation game on this graph. And so when we're playing the mutation game, sort of combinatorially, we'll start at one of these sorts of unit vectors where one of these vertices has a 1 on it and the other ones have a 0 on it. Now, in terms of the geometry or the coordinate system that I've just been talking about, we'd write this as B1, because B1, or, you know, to write it more explicitly, E1 take away E2, that's the vector associated with this vertex here. Now, let's say we update this system. Let's say we do a mutation at this central vertex here. Now, in terms of the mutation game, that's going to turn this into this kind of setup here, where we have ones now, because, you know, the way the mutation game happens is that this central vertex, the population there becomes negative, and then we add on the populations of its neighbors. So -0 plus 1 is 1. And so now after we've done this update, B1 has been turned on. So we have 1 times B1, but we also have 1 times B2 because that's been turned on. And so we could actually expand this out. It's E1 take away 2 plus E2 take away E3. And so on. So you can see that there's this nice sort of correspondence between the mutation game and this way of thinking about the system with vector algebra. But really, I think the most honest way to look at this is that when you do a mutation, let's say in this case at the second vertex, what you're really doing is you're taking a look at this vector here, B2, associated with the second vertex. That's a vector in 4D space. And then there's going to be a sort of hyperplane, a 3D hyperplane in this case, perpendicular to that. And then you're doing a reflection of your current vector. Well, it's this vector here. And then you're doing a reflection of your current vector, this vector here, in that hyperplane. So we could actually write this result as the result of doing a reflection in B2 perp on B1, right? Because here's the current population vector, here's the current population vector. Then we're taking that and we're doing a mutation on B2, meaning we're taking this vector here, we're taking the hyperplane perpendicular to B2, which is our second basis vector of the root lattice of D4. And we're taking this B2, we're looking at the hyperplane B2 perpendicular to that, and we're reflecting in that hyperplane. And the way the mutation game plays out, it sort of mirrors this geometric way of looking at what's going on. So I want to focus a little bit on this D4 lattice. So what is the D4 lattice? Well, it's the set of all quadruples of integers which add up to an even number. That's a nice, fast way to define it. But nice to think, what is the root system of the D4 lattice? And basically, that's kind of easy to describe. We could just basically say it's the permutations of stuff like this. Plus or minus 1, plus or minus 1, 0, 0. So, you know, we have points in 4D space of this form. If you look at all of them, how many of them are there? There's 24. And they are forming these vertices of this D4 root lattice. and this is a 24 cell. So this is one of the most amazing objects in all of geometry, all of mathematics, I dare say. I think people should teach kids about this when they're very young, because it's just very important, and it's very lovely. So here's a 3D print of this 24 cell. So it's a polytope. It's a 4-dimensional polytope. So a 3-dimensional polytope is just a polyhedron, right? A polyhedron has vertices, it has edges, and it has faces, which are 2-dimensional. A polytope in 4D, it's going to have vertices, edges, faces, and also cells, which are basically like 3D volumes. And in this case, the cells are octahedrons. So I have a little octahedron here, this 8-sided dice that I have. And maybe if you take a very close look at this, you can see that the cells here are made out of octahedra. If you look really, really carefully, you can see that there is a octahedron, a little octahedron right in the middle of this. I'm not sure if I can get a good angle. If you look really, really carefully, you can see that there's a little octahedron in the middle of this. It's not so easy to see. So, okay, I want to give you an understanding of the structure of the 24 cell. Firstly, I'll say it's an absolutely remarkable object. It is a Platonic solid. So, like the octahedron or the cube or the dodecahedron in 3D, it has this sort of perfect regularity. You know, all of its vertices look similar and so on. But it also has another absolutely extraordinary feature, which is that it is so-called self-dual. Okay, so what does that mean? Well, if you take a cube and you place a vertex in the center of every face of the cube, and you connect two vertices together when they have a common edge, and you just look at those new vertices and edges you've drawn, then you're going to get an octahedron. So the dual of a cube is not a cube, it's an octahedron. And that's normal, right? If you normally take a polyhedron and you dualize it, you usually get a different polyhedron. The only real exception usually is with a tetrahedron. The dual of a tetrahedron is a tetrahedron. Now, it turns out that this idea of dualization can be extended to high dimensional polytopes. And so if you have a polytope in n dimensions, then the highest dimensional kind of cell it's going to have is an n-1 dimensional cell, right? Like if you're in 3D, you're going to be looking at polyhedra, and the highest dimensional stuff they've got is faces that are 3-1 dimensional, and so on. And so to dualize a polytope, what you want to do is stick a point in the center of every one of those n-1 dimensional cells, and think of those as the vertices, and then connect a pair of them when the corresponding cells have an n-2 dimensional boundary, right? And so when you do this dualization process, it's like all of the n-1 dimensional stuff becomes 0-dimensional, all of the n-2 dimensional stuff becomes 1-dimensional, and you're sort of reflecting the dimensions of everything about the stuff that's sort of halfway up the dimensionality ladder. Anyway, so almost always when you do this, you get a different shape. The simplex is special. So the simplex is like a generalization of a tetrahedron. To form a simplex in n-dimensional space, you take n+1 points and you connect them all up by edges. And so it's a sort of generalization of the tetrahedron, and it's a Platonic solid, and it is self-dual. But apart from the simplex, being self-dual is extremely rare. But this is self-dual, and it's really a very extraordinary shape. So how do we get a 24 cell? How can we describe it? How could you make a model like this, for example? How would you know how it's structured? Well, I've already sort of told you enough information to figure this out, because I've told you that the 24 cell is basically the polytope that's vertices correspond to the roots of the D4 lattice. And I told you what the coordinates of those vertices are. There's things like plus or minus 1, comma plus or minus 1, comma 0, 0, and permutations of those things. So what does that mean? So basically what it means geometrically is that there's a way to get a 24 cell from a tesseract or a hypercube. So if you happen to have a four-dimensional cube lying around, like I do, you can easily get a 24 cell from it. And the basic point of all this is to form your 24 cell, you look at a hypercube and you look at all of the two-dimensional faces and you stick a vertex in the center at each of those two-dimensional faces. And then you link two of those vertices when those are sort of connected two-dimensional regions separated by an edge. And that's going to form your 24 cell. So that's basically how you can do it. Now, the way that you can see this is as follows. If you want to think about a hypercube, a really great way to do it is to think about all of the different things that you can write down made of zeros and ones that have 4 entries. So think about all of the sort of binary numbers that you can write down, which are full of zeros and ones. And then those are the vertices of the hypercube. So this one's 0, 0, 0. And then you go, okay, this might be the first direction. So this would be like 1, 0, 0, 0. And this might be the second direction. So this would be 0, 1, 0, 0. And this might be the third direction. So this would be 0, 0, 1, 0, and so on. So that gives you a sort of coordinate system. And it's just like a Cartesian coordinate system, but you're just looking at where the coordinates are 0 and 1. And so if you do that, what you've really got is a sort of unit hypercube, and you're basically just exploring around its vertices. So that would be a length 1 hypercube. Now, what I want to think about is a length 2 hypercube, and it's like the one I just described, except the coordinate system is a bit different. So imagine that the hypercube is centered at 0 now. So the old hypercube, I was saying the origin was at this vertex 0, 0, 0, 0. But now I'm going to get that hypercube, I'm going to make it twice as long, and I'm going to shift it. So now the vertices of the hypercube, rather than being these sort of binary things that are made out of zeros and ones, now they're made out of plus ones or minus ones. So if you think about it, the number of sequences you can write down made of minus ones and plus ones is the same as the number of sequences you can write down made out of plus ones and zeros. So we're looking at the same kind of structure combinatorially, but what we're really doing is we're thinking about the vertices of our hypercube now as basically being placed at these points like 1, minus 1, minus 1, 1, and all of the stuff like that, where all of the 4 entries are plus ones or minus ones. And so now you can think about what happens if you have 4 numbers, and those 4 numbers are either going to be plus 1 or minus 1 or 0. If all of those numbers are plus ones and minus ones, then you're going to be at one of the vertices of the hypercube. But if one of the numbers is 0, that means that you're in the middle of one of these cells or edges or faces or something. So suppose this is a vertex with coordinates 1, 1, 1, 1. And this has coordinates 1, minus 1, 1, 1. And this has coordinates 1, 1, minus 1, 1. So in this case, if you think about the point 1, 0, 0, 1, that's going to actually be right in the center of this one-dimensional face. So the point basically is that if you want to make a 24 cell, get a hypercube. Now, it's easy to make models of hypercubes. It's easy to draw them. I think it's quite easy to think about them. And then, you have all these two-dimensional faces. I could get this if I did this in washing up liquid. I think it would form these nice films. I'll probably able to do that for the video. But you can see that you're going to have all of these faces. And if you imagine that there's a vertex in the center of each of these faces, and then you just connect them up. For example, you'd connect this vertex here to this vertex here because there's an edge between these two faces, and you carry on like that, you get a 24 cell. Okay, so in fact, if you take this kind of projection of a tesseract and then you do this, you get this. So if I line this up right. I think that's the right way to line them up so that you can see this. So what's going on here? Well, what I'm really talking about, if you think of this as just a 3D model, I'm sort of dualizing parts of it because I'm placing a vertex in the center of each of these faces. So you can see that sort of as a 3D model, we have a big cube on the outside, a little cube on the inside, and then these yellow sticks here. And so when we do this process of turning it into the 24 cell model, these cubes turn into octahedra. The big blue cube is going to turn into the big octahedron on the outside of this model. The small blue cube turns into this tiny octahedron in the center of this. Yeah, you can see the little octahedron there, just sort of inside that triangle pointing downwards. You can see part of it. Well, anyway, I don't know if you can see it if I spin this round, but in addition to there being a small octahedron right in the center, there's a cuboctahedron in the middle. So the way that you can think of this, if you imagine this is like in spherical shells, right? So there's a point right in the center. There's nothing right in the center, but we can imagine a point right in the center of this 3D model. And then the first shell contains this little octahedron that's difficult to see. And then the next shell contains this cuboctahedron. So you can see it has triangles and square faces. It's going to have 12 vertices. And then the final shell is the big octahedron on the outside. And you can see now where those come from by the process I just spoke about. Because if you imagine taking this model of a hypercube here and placing a vertex in the center of each of these 2D faces here, well, that's going to turn this blue cube in the middle into an octahedron, this blue cube on the outside into an octahedron. And also for each of these 12 edges of the cube, there's going to be this sort of two-dimensional surface here that we're really going to place a point in the middle of when we're making this 24 cell. And so we're going to be adding these extra 12 points, and they're actually going to form a cuboctahedron shape. Because, for example, this vertex here is linked to this vertex here and this vertex here, and this forms one of these sort of triangles here of this cuboctahedron in the middle. And you can see that having points at coordinates like 1, 1, 0, 0, well, they're satisfying the properties that we want, right? They're integer coordinates which are adding up to even numbers. And you can see that those are the sort of closest ones to 0 that we can get. And this is, in a sense, why these points are forming the sort of root system of this D4 lattice.